in itself. And the chemical engineer is a central focal point of any project, because he knows the process, and from start to finish, the first document that is produced is by a chemical engineer in the project until the last commissioning of the plant. So chemical engineer is a central figure in any project team. And you may find process engineers in many companies. Some of them are operating production companies. Then you have supplier or vendor firms who actually supply, let's say, packages like a fire heater, a boiler. Then you have engineering consultancy firms, like, for example, Technip is there, Tyson Group is there. These are engineering consulting firms. Now, the process engineer can be in a business development, design engineering, or plant operations field. Now, process engineering emphasis. So again, as I mentioned, process engineers, let's say in operational production companies. So here they look after the, let's say they are in the technical services group, where they focus on modifications to the plant, or some revamp type job is occurring, or new projects are coming up. So they also have to be knowledgeable in process engineering, because they have to supervise the engineering consultants' work also. The process engineers who are in the engineering consultancy firms, they need to be very thorough in the process engineering of the equipment, as well as what documentation to be produced, because they are the actual central people who will do the project. And process engineers in OEM firms, like, for example, boiler manufacturer, fire heater manufacturers, they need to be knowledgeable in their own field. Yet at the same time, since they are part of the project, they need to also know what documents are required by the engineering consultants and how their package integrates into the rest of the system, rest of the project. Now, process engineering emphasis. Now, here I have explained. Now, suppose any chemical is produced by different processes. So if you say, let's say, ammonia and methanol, these are all produced by different processes. Yet what is common in all of these will be the equipments. So in all of them plants, you will have, let's say, pumps may be common, compressors will be there, fire heater may be there, you have distillation section, distillation columns are there, utility packages will be there. So what I'm trying to say is, it is good to know the process. Definitely the chemical engineer has to know the process technology, yet at the same time, he has to be very well versed in each and every type of equipment, as well as the packages that are involved, as well as what documentation is required, so that the project can be done properly without any hitches. So my emphasis always is, including the book I have written, my emphasis is on concentrating on the equipments as well as on the documentation. If you know this, you are in great shape. You can handle any type of project. So today we are going to discuss from that angle. Now, types of process plants. Now here, if you see, in a chemical industry, there are many types of plants. Some of them are continuous, let's say a refinery. Some of them are batch plants, like you have a small scale industry or a pharma plant, as I've shown in the figure. So as you can see in the pharma plant, these are SS equipments, because they have to be quite clean. It's a pharmaceutical industry. Yet at the same time, these are batch reactions. So you can see the reactor is a batch reactor. So each and every type of plant has its own challenge. In the continuous plant, the challenge is different. In a batch plant, the challenge of a process engineer is different, because you have to ensure that the batch additives are being given to the batch in certain time duration. The batch occurs in a certain time duration. Then you have to dump the batch to the next step. So all these things are part of the sequencing in a batch plant. So each and every process is different, and one has to treat each process differently. Similar to that, now I've just categorized the types of chemical plants. On the left, you see the continuous plants are there, and on the right are the batch plants. So just for your information, each and every plant has a different methodology with which you have to attack the process engineering. Again, I'll just say a small scale industry, for example, may run 16 hours a day, 8 hours it may be down in the night. So one has to accordingly design the system. Whereas a refinery, you cannot do that. The reliability has to be very strong in a refinery. Okay, now project types and stages in CPI. Now, why I'm going to cover the project types is because process engineer, when he's working, he needs to know what type of project he's working on, because his mindset and the cap which he puts on his head has to be accordingly oriented. Now, for example, following types of project contracts usually made in the chemical process industry: cost plus fee reimbursable. So what exactly is this? I'll give an example. I had worked on a project through my earlier company for a customer. that customer had transported a plant producing a certain polymer from France, where it was lying idle for many years. Along with the technology purchase, he had shifted it to India, and he wanted to set up the plant in India. Now, this plant was a very old plant. It was lying stagnant for many years. So what this means is that if the engineering consultancy is taking up the job, he does not know the exact quantum of work involved. Maybe certain pump which has been brought from France to India, that pump may or may not run. So if it doesn't run, you have to again procure a new pump. So that means the effort has to go into the procurement activities also. So what this means is that the contract was taken on a cost plus fee reimbursable. So it was actual man hours reimbursable basis. And once the definition is brought, then you can take it on the other types of contracts. Now the EPCM is Engineering Procurement Construction Management. I will elaborate on this in the next slide, where the clarity will be there. EPC also is in the next slide. It will give you a better picture. PMC, Project Management Consultant. Now, let's say consultancy has made a feed document, which is a front-end engineering design document. I will explain all these types of documents. Please don't worry about it now. So when the feed document is produced, the feed document goes in the next stage of the project, which can be EPCM or EPC. So what happens is normally the client has a very core team. So that is called a project management team, PMT team it is called. And the engineering firm who has made the feed package, he becomes a project management consultant. And he basically supervises the engineering contractor's work to ensure the quality of the deliverables, technical quotient of the deliverables, all is ensured. Then the engineering can be feasibility study, which is a detailed feasibility study, DFR, what is called. Pre-feed engineering, again, I will explain in each type what is required. BDEP is a basic engineering design package. Feed is front-end engineering design, detailed engineering. Projects can be Greenfield or Brownfield. Now, as I explained, the EPC contract. Now, EPC contract is an engineering, procurement, and construction related contract. You can also have the EPCC type, which is a commissioning also is included. These are lump sum contracts. The risk portion is very high for the engineering consultant. So as you can see, the owner has nominated the EPC contractor. It is the EPC contractor's job to award to the engineers, consultants, suppliers who are the OEM package suppliers, and then the other contractors like the site erection contractors, civil contractors, E&I contractors, electrical and instrumentation, mechanical contractors. So the entire risk for the completion of the job lies on the EPC contractor. Now this is a very risk-based EPC, and many companies have gone bankrupt. Like for example, I had worked in Shaw Group, which was taken over by Technip. Shaw lost heavily in an ethylene job in which they had taken an EPC contract. So somehow it exceeded far above what they had contracted for, and they had to go bankrupt and taken over by Technip basically. So EPC contract is a lump sum turnkey contract, and the risk factors were quite large in this. But to the owner, it is very good because it is his responsibility becomes less. Everything is taken over by the EPC contractor. Now EPCM contract, as one can see, the owner on the right-hand side is the EPCM contractor who is doing the engineering, procurement, construction management, and the owner gives the orders and the procurement for the suppliers, construction contractors, other contractors. Now, the difference between these two I want to elaborate and how a process engineer has to look at it. A EPC contract, whatever has been costed on which the company has bid for, the EPC bid, that has to be engineered. You cannot have too much gold plating. So if you want, if the client, for example, insists on adding 5 equipments, all of that comes at a cost. The EPC contractor does not have that luxury. So basically, it is a fit for purpose plant. So the process engineer has, when he is doing the engineering, has to be careful not to overrun the expenses drastically, because ultimately it is a lump sum fee, lump sum cost. Whereas in the EPCM contract, you can have some gold plating. These are man-hour based, man hours as well as the construction man months. So there some amount of gold plating can be acceptable. Change orders can be raised. If the owner does not give that also, fine. It's not a big loss to the company, but an EPC you have to be very careful. So gold plating is not allowed. So that's how a process engineer has to view these different contracts. Now Greenfield versus Brownfield. Greenfield basically, as the name suggests, it is a totally grass is there on the site, grass vegetation. So you have to clear it and then you erect the new plant. So that is a very straightforward plant. Everything is new, and relatively the easiness of the project is also there. Brownfields are far more complicated. So brownfield job involves many things, and the process engineer has to be very careful. For example, in the P&IDs, for a brownfield job, you may have to tie up to the existing many utilities, etc. Firefighting network one has to tie up with. So all these have to come in the P&ID. So there is a demolition P&ID as well as a new P&ID for the new tie-in point. Plus the brownfield job, for example, some existing vessel or pump may have to be used. So the adequacy of that existing vessel or pump has to be checked. For example, the existing flare system needs to be used. So that existing flare system adequacy needs to be checked. So there are many more complications in a brownfield project as compared to a greenfield job. Now we go to the next slide. Now various stages of the process. So various stages of the project basically comprise. Now it depends on the what the owner actually wants. And maybe he wants you to do only the feed engineering. Fine. So then the feed engineering needs to be done. Particular projects may encompass the whole steps basically. So you have the assess stage, which is called conceptual. So in the conceptual stage, a project feasibility and alignment with business strategy is made. Here the process engineer is the central figure, not many other disciplines are involved. I will show you the documents which are there in this stage also. The accuracy of the costing required is plus minus 50%. Now please understand that all of these stages are gated processes. So the customer is looking for a cost for which he can then go into the next stage. Maybe he has to approach a bank, maybe he has to take out a bid in the market so that shares can be put out and he can get funding for that. So these are all cost has to be done at each and every stage. Now select stage is pre-feed stage. The documents I'll share in the next slide, which will make it very clear to you. Costing is plus minus 30%. It's become finer now. Defined stage is the feed engineering. Okay. So here, if you can see, the customer is actually getting the project funding. Cost is become plus minus 10% accuracy. It's quite high. And then execute is the detail engineering phase where actually the procurement occurs. Okay. It can be EPCM based, it can be EPC based, but the actual procurement occurs in the detail engineering stage. So now here are the documents as you can see. The first column is the assess. Now in the assess, if you see, the documents are quite raw because the accuracy level is plus minus 50. So here if you see, only the block flow diagram is made. Process flow diagram is not there. PFD is not made, only block flow diagram is made. No P&ID is made. Okay. Then the equipment list is of the major items only. In the select phase, which is the pre-feed, some more definition is brought. For example, process flow diagrams are preliminary, some preliminary P&IDs are made. So this is how the thing goes. In the defined phase, which is the feed engineering. Now feed engineering, not only process, other disciplines get involved because you have to go to plus minus 10% accuracy. So the process engineer has to generate enough documentation so that the other engineers, other discipline engineers like civil, mechanical, electrical, instrumentation, then you have technical safety, piping, all of these get enough definition so they can also do their engineering for the feed and then take out the material takeoff, which is called MTO for the costing purpose. Okay. In feed stage, again, procurement is not done. That is very important. Duration of a feed for a large project is roughly 5 to 7 months. So in the defined stage feed engineering, as you can see, the process flow diagrams are optimized, process P&IDs are and the equipment list, etc. are complete. And execute also is a detail engineering, so everything has to be complete. P&IDs are issued for construction. Now we go to the next stage, engineering disciplines, codes and types of equipment in CPI. These are the core disciplines as I've written down. I will not go into depth with the interactions in each. This is an introductory webinar. In my advanced course, I'll be covering this in depth also. Process, mechanical, instrumentation, piping, electrical, civil, technical safety, all of these have a role in the project. Support disciplines are also there, business development, project management, project control, and estimations group. Now we go to the various codes typically used in projects. Here you can see, in India, normally the projects, as well as Gulf countries, we normally follow American codes. The ANSI code is American code, API is American code, ASME, ASTM, these are all American codes. Here you see also DIN is there for the German. So in Europe, maybe if you are doing a project in Germany, DIN standard is applicable. And then on the right-hand side, if you see, IBR is there. This IBR is mandatory for India for steam and condensate services. SO is there, which is also mandatory for certain chemicals. Like for example, if you are handling LPG, liquefied petroleum gas project, or LNG, it comes under the PESO rule, mandatorily comes under PESO. So these are the various standards. Here at the bottom, you see OISD, which is Oil Industry Safety Directorate. This is also to be followed mandatory in India for refineries, upstream oil and gas projects, etc. Now, few major equipments and utilities in CPI. I will be giving a break, 10 minutes restroom break, maybe after 2 hours. So please hold till that time. Few major equipments and utilities in CPI. Now, in the equipments on the left, you see few equipments are listed. We will be going through all of these briefly. And on the right are the utilities, which are there in any plant. Firefighting system at the bottom is done by technical safety, but don't worry too much about it. You just understand it's there basically. The rest of the systems I'll be elaborating upon. Now, pumps. So let's start with the pumps. So the type of pumps, there are many types of pumps. On the left, you see centrifugal types are there. Then on the right, you see positive displacement types are there. Rotary types are there. And you have some special types like progressive cavity, concrete pumps. Each pump has a specific area of application, which we'll cover briefly. Centrifugal pumps normally occupy around 80% of the industry pump types. So we'll start with the coverage of different types of pumps. As you can see, the capacity is on the x-axis, on the head is on the y-axis. So when the capacity is low, you enter into the metering category, which is the positive displacement pumps. On the right-hand side, you see the axial flow with a very high capacity, low head pumps. These are very high capacity pumps, axial pumps, but the low heads are very low. So these are the overall nomenclature of the pumps. Now we'll cover the difference between dynamic and positive displacement pumps. So here you can see the first column is positive displacement. So as is a clear screw pump, gear pump, reciprocating, progressive cavity, these are positive displacement pumps. They are constant volume and basically they operate on back pressure principle. So the more the back pressure, again they will push more and more, unlike a centrifugal pump. So as you can see, the characteristic curve is there's a single flow straight line and the differential head can be anything. It depends on the back pressure. So more the back pressure, pump will keep on building until either the casing breaks or maybe safety valve activates on the discharge side. Whereas a dynamic pump, which is a centrifugal pump, has a different principle. So it increases pressure by using rotary plates to increase fluid velocity, which converts into pressure head in the casing. So this is the performance curve as you see at the bottom. So this is the typical centrifugal pump performance curve. The arrow is the design point, okay? Certain design point, which is a best efficiency point, BEP, what is called. Now the pump classification is as shown. So on the left, you have the centrifugal pumps, which are again, many types are there. And at the bottom, you see the special type of pumps are there. Jet is there, gas lift, hydraulic ram, electromagnetic. And on the right-hand side are the displacement, positive displacement type of pumps, which again are many types. Diaphragm pumps are in the middle, which have a Teflon diaphragm in the middle. So that protects the non-process part. And these are very good, like AODD pumps, air-operated double diaphragm pumps are very frequently used for drum unloading, etc. And rotary pumps are there at the bottom. Screw pumps, gear pumps. We'll discuss this in detail also. Selection of pumps. Now the process engineer, while selecting pumps, has to look at a few categories. So capacity, total head to be developed, physical chemical properties of the liquid. Then just I have written down some services and the type of pump. This is a very brief table, but for your understanding, it's good. So high flow, low head pumps, centrifugal are good. Medium flow, medium head, rotary pumps are there. Rotary pumps basically are like screw pumps, gear pumps, vane pumps. Then low flow, high head pumps. Here you have reciprocating or diaphragm pump. And there's a very special pump called sundyne pump, which is a centrifugal pump, inline pump, which operates at about 10,000, 12,000 RPM. It's a very specialized pump, centrifugal for low flow, high head categories. But they are very expensive also. Then metering small flows, you have a plunger pump or a positive displacement metering pumps also are there. Then we come into centrifugal pump fundamentals. So as you can see in the diagram, the fluid enters in the suction on the left-hand side. Suction nozzle is there, A is there. Then it is through the impellers. It basically translates the velocity into different head and then the discharges on the outlet. So this is a typical centrifugal pump. Impellers are of different types. I'll come to that also. So you have two types, axial flow pump and radial flow pump. So majority of the types you'll see are the radial flow type, where the impeller is there. On the left-hand side are the axial flow pumps. These axial flow pumps are low head and very high flow capacities. Now, recently we had done a project for one of my past companies for a client. So the reactor had to have continuous circulation of the chemical to a cooler. So an axial pump was employed because it was basically a complete circulation and a head was very less, but the flow rate was huge for the exothermicity to remove the exothermicity. So that's a typical example of the axial flow pump. Now, important process parameters to be specified for centrifugal pump by the process engineer. As you can see, code to be followed. API, ANSI, Hydraulic Institute. API 610 is the code. These are very robust pumps. They are run for many, many hours without failure. ANSI pumps are smaller for chemical services normally. And API pumps are almost 1.5 to 2 times costlier than ANSI. Hydraulic Institute standards are followed for very high pumps where, for example, cooling water pumps, where you have very high flow rates and let's say 50 mLC head meters of liquid column. The Hydraulic Institute standards are followed. Manufacturer codes are followed for plastic pumps. So you may have a PP pump, polypropylene, or a WM/HDPE pump. So ultra high molecular weight PE pump, where the manufacturer codes are followed. And as you can see at the below, these other properties are there. All of these has to be specified by a process engineer. Now we come to a centrifugal pump minimum flow protection. So centrifugal pump, to avoid cavitation, there is a minimum safe flow, MCR what is called. That has to be ensured the flow is always above that. So there are two ways you can do it. One is you can have a restriction orifice going back, as you can see on the left hand figure. So this restriction orifice, now important thing to remember here is the flow through the RO has to be added to the capacity of the pump. So if you have a 5 meter cube requirement in process, if the minimum flow through RO is 1 meter cube, the capacity of the pump becomes 6 meter cube. Please remember this. On the right hand side is another way of doing it through a control valve. This control valve is normally closed. It will open only when the flow senses, let's say 5 meter cube is there, 1 meter cube is minimum flow. So it will open only when the flow goes below 1 meter cube, and it will ensure that 1 meter cube is always there on the pump to above the minimum flow category. So that means the pump now has to be ordered for 5 meter cube only. So that's a fundamental difference between these two types. The impeller types. Here you can have open, partially open, enclosed. As I've written down, open impellers are used for services with solid particles. Let's say sewage is there. Semi-open impellers can be used for intermediate abrasive fluids. And enclosed impellers normally occupy a majority of the services. 80-85% are enclosed type. They give better efficiencies and they are for clean services only. Now, centrifugal pump affinity laws. So, as is aware, the flow rate varies proportional to diameter as well as speed of the pump. The head varies square of the diameter or speed changes, and the power varies cube of the diameter or speed changes. So with this, if you are having any speed change in the pump, you can automatically calculate the other parameters. These are called the affinity laws. Now, impeller specific speed in centrifugal pumps. This process engineer normally does not look into this, but for your information, I have kept it. Depending on the type of pump, you see the specific speed is varying. Okay, with the axial pumps on the right hand side. This is not important, so don't worry about this too much. The next slide is important, which I'll explain to you also. So NS is an indicator of the impeller geometry and discharge characteristics, what you are seeing just now. And the suction specific speed, which is the next slide, is important for process engineer. We'll go to that slide now. So this is a suction specific speed. Now suction specific speed indicates the suction characteristic of the pump. So as you can see, the formula is S is equal to N under root Q divided by H. NPSHR is to 0.75. Okay. Now, in any pump, in a feed stage engineering, let us say you are asked to give to the other disciplines what is the height of the suction vessel, how high it has to be, whereas you don't have any reference to any vendor interactions, and you are not sure exactly how much NPS is available to give to the pump. So in that stage, this particular formula comes in good use. Now, there's a certain upper limit which needs to be maintained. In the 1980s, a lot of refineries and all, they used to keep very high suction specific speeds. So that used to give a very low NPSHR. What this basically means is that the suction vessel height comes down. So you are saving in the capex of the structures, etc. But then the pump started giving a lot of problems. Investigation was done, and this bottom criteria was established. So now UOP, for example, keeps a higher limit of 11,000. They don't go above 11,000. I would give you, I would say, go with a conservative value. 7.5 to 8,000 in the American units should be the suction specific speed. With that, you can calculate the NPSHR required in case you don't have access to any go-by data vendor interaction, and you can plan your feed engineering with that NPSHR, keeping 1 meter to get the NPSHR available. So here the process engineer as a last resort can use this formulas. Now centrifugal pump. Now there is a very specific tendency of a centrifugal pump, which I think not many people may not be aware of. The impeller of a centrifugal pump, if it is designed for 100 feet, will build 100 feet irregardless of the fluid density. So if you have a fluid density of, let's say, gasoline 0.75, it will still give 100 feet. The discharge pressure in PSI will be very different. Water will give the same 100 feet. Brine of 1.2 will still give the same 100 feet. Okay. So what this means is that if a gasoline, if you are designing an impeller, let's say a pump for gasoline services, when you retrofit that pump for a brine service, you have to be careful. Number one, your discharge pressure will be higher. So is your discharge piping suitable for that? Number two, the power drawn by the pump will be higher. So your motor should not trip. So the impeller will still try to build 100 feet. So this is an important thing one should remember for brownfield jobs. Now these are the types of pumps of centrifugal pumps. So as you can see, A is the steady fall, B is the steep curve, and you have the flat curve, C. D and E are unstable curves. So for stable performance curves, there exists only one flow rate for each value of head, as is seen in A, B, and C. Okay. For unstable performance curves, there may be 2 or more values of flow rates for each value of head. So D and E are unstable. Okay. So unstable curves, like in E, for example, are usually the result of very high specific speeds. The formula we saw earlier. Usually, good engineering practice dictates that shutoff head should not be more than 20% over design point. This is a good engineering practice. You don't want a very steep curve as in B category. Okay. And pump should ride in a flat manner towards shutoff. So a pump is the best out of the whole lot, basically, because it has a falling curve, but not very steep also. So these are the things one should remember: performance curves, head versus flow rate. Now there's a typical performance curve of a pump. So as you can see on the bottom, right at the bottom, we have the NPSHR, which rises as the capacity goes up. The shaded area is the design point. On each line, we have written the impeller diameter. Okay, so any casing has a maximum impeller diameter. So there is some flexibility of going higher in the impeller diameter and the head. If you are stuck, let's say, in the detail engineering towards the end, you can go slightly higher on the head also. And the efficiency curve is there. As you can see, the shaded portion is almost at the BEP point, best efficiency point. Now on the left, you see a MCSR. That is minimum continuous safe flow, MCSF. So this is the minimum flow of the pump. And the power, as you can see on the right, this is a typical performance curve of a pump. Now centrifugal pump calculations. So the suction pressure is vessel pressure plus static suction height minus friction drop on the suction line. NPSHA is suction pressure minus vapor pressure of the fluid at that fluid temperature and pressure. NPSHA to be greater than NPSHR by minimum 1 MLC, 1 meters of liquid column. Differential pressure, always in centrifugal pump, you give differential pressure. So the discharge pressure minus suction pressure. The hydraulic power formula is there, and the pump BKW is a brake KW. So you have to divide by pump efficiency, N, eta. So always remember NPSHA to be calculated in absolute units. Now these are the PD pumps now we'll go to. So there are many types of PD pumps, as can be seen. Each has a different application. So for example, you see the single screw pump in the middle. This is specifically used for a large fuel oil network, where you have a very large, let's say 5-6 fire heaters are there, and you are supplying fuel oil to burning of each. So then there's a large fuel oil tank, and then this a single screw pump is there. I will be showing this in the utility section. Similar to that, for example, you have the Squeegee Pump, which is called also called peristaltic pump. So this peristaltic pump is used in high solid services, like if you have latex, In my previous company, we had handled 80% solids in water, polymer latex. So there, this Squeegee pump is very good for that services. On the right, you see a sliding vane pump. This vane pump can also be used in the dry mode to get a vacuum. So it gives good vacuum also in the dry mode. Again, the chart I'm repeating. So as you can see, these are the different pumps. You see metering plunger, metering diaphragm, gear pump is there. Okay. Then process data to be specified for PD pump. So these are the type of process data the process engineer has to give. Okay. Now the non-centrifugal pumps applicability, flow and head. So as you can see, the class of the pump, the type of the pump, the maximum flow. These can change a little bit vendor to vendor, but these give you a good idea overall. And the head produced in PSI. So reciprocating, as you see at the bottom, very high heads are produced, 10,000 PSI, for example. Okay, so reciprocating pumps are always used for very high head services. Then the suction calculation, the calculations for PD pump. As you can see on the top, suction pressure is similar to centrifugal, only the new acceleration head is added because the PD pump has a pulsating flow. So if you see a metering pump, you'll have flow going in, stopping, coming, stopping, coming, stopping. So that's why this acceleration head is introduced. You have to minus that in order to get the suction pressure. Otherwise, the formula stays the same as for the centrifugal pump. Now, typical characteristic of PD pump. As I mentioned earlier, flow rate and head is a very vertical line sort of, because the positive displacement pump always operates against the back pressures. That's why the PD pump data sheet always discharge pressure is mentioned. You don't mention a differential pump. Differential head like a centrifugal is not mentioned. Then introduction to pump hydraulics. Now hydraulics can be many types. Gas hydraulics are there, vacuum hydraulics are there, two-phase hydraulics are there, pump hydraulics are there. Here I'm just covering in brief for the pump hydraulics. In the advanced course, I'll be going very deep into this subject also. So in pump hydraulics, we calculate the pump suction pressure, NPSHA, and pump discharge pressure. NPSHA is important, again, as I mentioned earlier. Operating conditions and liquid properties as per process flow diagram and heat and material balance. Design flow is estimated as per agreed design philosophy. So design flow, basically what I mean is how much excess to keep, what design margin to keep. This is decided in the basis of design, which a process engineer makes at the start of the project. Then process calculation sheet hydraulics. So again, these are the steps one has to follow. Routing sketch is drawn for proper understanding of system before hydraulic calculations. The plot plan has to be followed for starting from the pump to the end vessel, how much distance is there. So in feed or in initial detail engineering, one has to visualize the routing part. Okay, later on you will have exact isometrics towards the final pump head verification. Now discharge pressure, etc., is estimated using, I already have a line sizing template. One can use that. One can also use many empirical formulas are there for the pressure drop calculations. Then the flow rates are there. So the flow rates, again, generally reported normal, maximum, minimum. These are very much required for control valve. Control valve has to calculate the CV at 3 different points: minimum, normal, maximum. Okay, and the last point again I have mentioned here, all pump hydraulics have to be revalidated against the actual isometrics later on in detail engineering. So the final impeller head can be established. Now service margins on centrifugal pump capacity. These are mentioned in the basis of design document at the start of the project. As you can see, reflux pumps. So 20 to 25% margin should be kept. So let's say your reflux flow rate is 1.2 of your distillate flow rate, for example. So then you keep accordingly 25% more, so that you have flexibility in column operation. Whereas, for example, a recirculation pump, example, tempered water circuit. As I had mentioned, the earlier exothermic reactor, the axial pump goes to the cooler. You don't want to keep any extra capacity. You can have 0% capacity there. So these are the industry general engineering practices, basically. Normal pumps you keep around 10%, as is shown on the top. Hydraulic calculations, now we come to the static head. So the static head, basically, to determine the suction and discharge static head, the liquid level in the suction and discharge vessel has to be considered. The pump suction nozzle elevation has to be considered. So these are the norms, basically. So minimum level in suction and maximum level in discharge vessel shall be used as guideline. In the suction side, bottom tangent line, tan line, what is called, of a vertical vessel. or the bottom line of horizontal vessel to be considered. These are good engineering practices. Pressure drop in the line. So again, here as I mentioned, these are the normal control valve delta P's used. Now here I want to elaborate one thing that is very important. See, one has to understand that a control valve is like a pressure drop bank. A small bank cannot run a large nation's economy. However, a strong bank like a Reserve Bank of India in India can help run the India's economy because it has sufficient clout in terms of size. If the system needs more pressure drop, then selected control valve should be able to give up some of the pressure drop by opening up more without being compromised on performance. Similarly, if the pressure drop in system decreases over that designed for, then control valve should be able to absorb some pressure drop. That's why you need to give some decent delta P to the control valve. If I give 5% of the system drop, that control valve is not going to be able to control properly. Okay, so we need to understand this when you are designing control valves. Then these are some pressure drops I've kept in the slide. For example, a suction strainer on a pump, 0.07 bar. Heat exchangers, tube side normally 0.7 bar. Shell side you can keep lower, 0.35 to 0.5. Air cooler 1 bar. Fire heaters you can go up to 2 bar through the coils. Filters normally 0.7 bar. Resin beds, multi-grade filters for water services you can take up to 1 bar. Instrumentation, as you can see, these are the varying pressures which normally one takes in the hydraulic calculations. Now compressors. So we'll go to the types of compressors. So as one can see on the left, dynamic compressor, centrifugal axial. On the right hand side, the positive displacement, which is reciprocating piston diaphragm, rotary, which is screw, lobe, liquid ring, sliding gate. This diaphragm compressor is an important compressor. Nowadays, the hydrogen has picked up a lot of speed. Everybody wants to make hydrogen, which is a green energy from water. So there, the hydrogen fueling stations are there, which operate at 700 bar, etc. In India, we have about 350 bar right now for the fueling of the vehicles. So there, the diaphragm compressor is used. It can build up use hydrogen to very high pressures, about 450 bars, etc. Then a brief comparison between centrifugal and PD compressors. So this is a brief comparison, centrifugal and positive displacement, and can be seen. Important is the non-lubricated nature of the centrifugal compressor. In PD compressor, you can have both available. You can have lubricated as well as non-lubricated. So the reliability is very important parameter. Centrifugal gives the most reliability amongst all. Okay, and then the oil-free screw compressors at the bottom also give good reliability. These are used in instrument air and plant air services, and also in some polymerizable gases services. Here I have given a brief comparison between various compressor types. Reciprocating compressors, as you can see, lower reliability, smaller capacities, very high discharge pressures. The piping has to be very well supported for the pulsations. Foundations have to be strong. Centrifugal compressors are constant head machines. They are similar to a centrifugal pump basically. They can have very huge capacities. They are not economical in small capacities. They have a surge limitation at turn down. So if you, I have seen a compressor when I was in Sabic, Saudi Arabia, surge, and it makes a horrible racket. You cannot stand there. So one has to always operate above the surge limitation. Reliability is very high and they're low maintenance. And screw compressors. Now wet screw compressors have very high efficiency and very high pressure ratios. See, normally if you see oil-free screw compressor may have a pressure ratio of 1:3, 1:4. Oil injected, because the oil acts as a cooling media, you can go up to 1:23 pressure ratio. Okay, but however the oil is there on the discharge, so you have to be careful. You have to have special filters on the discharge. The dry screw can tolerate polymerizable and dirty gases also. Okay, this is very important for the screw compressor. The coverage of the various types, as you can see. So on the smaller capacity on the left is the reciprocating type. On the right hand side are the eggshell type for very high capacities. Process engineer inputs for the compressors. So as one can see, these are the inputs one has to give for the mechanical disciplines and the manufacturer to quote accordingly. Same for the specific considerations while preparing PDS of the compressor. So the specific considerations like safety attributes, over design factor, compression ratios, process staging, etc. has to be provided. Sparing philosophy. Now the curves of the different compressors. So one is the pressure on the left and flow is on the x-axis. So as one can see, reciprocating is pretty vertical, as is expected, same as a PD pump. The centrifugal is similar to a centrifugal pump, and the axial also is similar to a centrifugal pump, but a steeper slope basically. Compression limits. So this is important. So reciprocation and reciprocating compressors, as you can see, very high discharge pressures you can have, about 5 compression ratio per stage. The centrifugal compressor has about, you can see, up to 10,000 one can go. Axial flow, the delta P is very less. So 1.2 to 1.5 on the compression ratio. And the centrifugal compressors are always polytropic in nature. This is very important. Okay. So the centrifugal compressor and axial compressor are always polytropic in nature. They have more loss on the enthalpy side than reciprocating compressor, which is isentropic. So as one can see, the interrelation of the polytropic N coefficient versus isentropic K coefficient is shown in the formula below. Now the centrifugal compressor performance curve. This is pretty similar to a centrifugal pump performance curve. As can be seen, on the left-hand side is the head, on the x-axis is the volume, and you have the different speeds. So RPM speeds are there. The performance curve is there, and the surge limit is there on the left. Best efficiency point also you have to see where it falls into. Axial compressors. Now axial compressors are normally used for compressing air or nitrogen. For example, gas turbines. You have to have an air compressor in it. So axial compressors are very good for those services. They have about 8 to 10% higher efficiency than centrifugal compressors. Okay, but they cannot be used for very high pressures. So they are limited to these two services. A performance curve of an axial compressor at different speeds. Reciprocating compressors. So reciprocating compressor basically is a adiabatic compression device. Centrifugal axial compressor converts velocity head to pressure head, thereby utilizing dynamic characteristics compared to positive displacement mode of reciprocating compressors. So reciprocating compressors are isentropic, adiabatic, and reversible, while centrifugal and axial compressors are polytropic. Polytropic path consumes more enthalpy than isentropic, okay, owing to the higher hydraulic losses incurred while transferring velocity head into pressure. So you need to remember this, okay. Now here one important thing, the recip compressor, you see the point number 3, gases with low molecular weight below 15. This is very important. And it can handle different molecular weight gases in the same service also, as long as your motor is sized for the different gas molecular weights. The parts involved in the reciprocating compressor. So on the right, you see the main discharge head. You have the piston moving in it. Flow is from the bottom, discharge on the top. And you have a piston. So at the left-hand side, you have a flywheel, which is rotating and pushing the piston in and out. So this is a single-state typical recip compressor. Now, rotary compressors. So rotary compressors are 4 different types: lobe type, sliding vane type, liquid ring, and screw types. The sliding vane also can be used as a vacuum pump. Liquid ring type is also called LRVP, liquid ring vacuum pump. So liquid ring type is a very good vacuum pump also. Okay. So these are the rotary compressors. Now we come to the fans and blowers. So fans and blowers basically are, they provide air for ventilation and industrial process requirements. So fans generate a pressure to move air against resistance caused by ducts, dampers, etc. So we will discuss this in the next slide. Okay. So now the difference between fans, blowers, and compressors. So as per ASME, following differentiation is made depending on the specific ratio, the pressure ratio basically, and rise in system pressure. So fan, you can go up to 1.11. So atmosphere is 1, you can go up to 1.11. So the pressure rise as in mm water column is shown here. Okay. And the blower is 1.11 to 1.2. And the compressor basically more than 1.2. So this is the basic differentiation between the 3 types. Now types of fans and blowers. So these are the different types. Centrifugal flow fan is there. Axial flow fan is there. Axial flow fan is nothing but the exhaust fans we find in our house or warehouses, etc., which are very low head axial fans. Major blower types are centrifugal blower and positive displacement blower. Positive displacement blower is also called a roots blower, which is very highly used in pneumatic conveying applications. So centrifugal fan, as you can see, are 3 types: radial, forward curved, backward curved, and so certain other characteristics are shown here. Axial fans are, as I mentioned, very low head. You can have different types here: propeller axial fan, tube axial fan, vane axial fan. Blower is there, which is used in pneumatic conveying services, as I mentioned. So here you can see centrifugal blowers are there, and positive displacement blowers. So this can be used to blow clogged materials free. So this is definitely the roots blower category used for pneumatic conveying applications. Then fans and blower process data sheet. So these are the different things that a person has to give, process engineer has to give for fans and blower process data sheet. So if the blower or fan is taken suction from atmosphere, the process engineer, he or she, has to specify the ambient air, meteorological data also. So ambient temperature, the barometric pressure, all this also has to be specified there. Then I will go to the next one. So fire heaters. So in the fire heater category, fire heaters are very important pieces of equipment. They are very complicated, and it is not easy to design these. They should always be left to the expert OEMs, original equipment manufacturer. But I will still give the process engineer has to have still idea so that he can intelligently interact with the OEMs. Okay. So my purpose in this is from that angle. So fire heaters basically can operate in different modes: natural draft, induced draft, forced draft, balanced draft arrangements. So I will be elaborating on this again. Now this is a typical balanced draft fire heater. So as you can see on the right hand side, you have the forced draft fan, which is sucking air from the atmosphere, pushing it through an air preheater into the air ducting to the main firebox. This is the radiant firebox, what is called. At the top is called the radiant arc, just below the crossover. Okay. This radiant arc is where the draft is measured always. The shock tubes are below the convection section. The three bottom tubes are called the shock tubes. They are not finned. Above that starts the finned section, which is the convection section. And above that, you can have a preheater also for the water. And finally, the flue gas ducting goes into the APH and out through the ID fan. So this is a balanced draft assembly. This gives maximum efficiency. So fire heater codes applicable. So these are the various codes applicable for a fire heater. So API standard 560 is the fire heater for general refinery services. There's a DIN 4574 at the bottom, which is normally used for small hot oil heaters. It is roughly 30-40% cheaper than an API heater, which is a very large heater. So fire heater applications, as you can see, many types: column reboilers, fractionating column feed preheaters, reactor feed preheaters, heat supplied to heat transfer media, hot oil heater, what is called, heat supplied to viscous fluids. Let's say a storage tank farm is there, you need to keep it at a certain viscosity. So you have a fire heater there also. Fire reactors are there. Now two types of fire heaters: the direct fire heaters, which normally you encounter in the process industry. So directly the process coil is there inside the fire heater, and you are heating with direct burning of the fuel. And the indirect fire heaters. So these are called bath fire heaters. So the fire heater basically is having the burner, which passes the hot flue gases through a ducting and out through the exhaust. The hot flue gases, flue gas duct is inside a water bath. Inside the water bath is also kept the process coil. So this ensures that the process coil will never see temperature above 100 degrees centigrade. So this ensures you are not overheating the process coil. That's why many times, let's say you have cryogenic propane, you are heating the propane. So at the end, they have a water bath to heat it to atmospheric temperature, ambient temperature, and they normally go with the water bath assembly. So you don't ensure overheating of the propane, etc. Now the different types of fire heaters are there. One is on the left, all radiant type. This is a very low efficiency. There is no heat recovery. Efficiency is maybe 60%. Only radiant section is there. On the these are for small services. On the middle, you see the vertical cylindrical helical coil. Now there are two types of fire heaters: vertical and cabin type. So we'll discuss both. We are talking about vertical type now. And on the right, you see vertical cylindrical. Now each has its own capacity limitation. So different pros and cons are there for each. Then you have the vertical category, three more: vertical cylindrical with integral convection section, the arbor or wicket type in the middle. The UOP always uses this type for their charge heaters, because arbor or wicket type normally have very large gas flow and very low pressure drops. So that's why these type of heaters is used there. Now vertical single row double fire type. So now you need to be a little bit careful on these. Reason why I said the OEM has to design this is the burner flame should not impinge on the heating coil. That's not good. So that is why always you have to remember original burners which were there maybe 40-50 years back, the flame length is a certain. Ultra low NOx burners which are there predominantly now have a flame length 2 to 2.5 times of that. So that is why these things were, for the design aspect, it is best left to the OEM because the burner flame and all is very important in this. Now we come to the cabin type. So different cabin types are there, as you can see. On the left, you have the cabin, simple cabin. On the 2 cell boxes there, cabin with dividing bridge wall. Each has a different capacity range. Again, 3 more types of cabin types are there. Again, the pros and cons are there for each and every type. Now the comparison with cylindrical and cabin type, the overview of comparison. So cylindrical types heaters occupy smaller slot area, have larger sizes, lower cost, taller firebox, more draft at the burner, flue gas velocity higher in convection section, gas film coefficient is higher because of that, and can accommodate more parallel passes in process coil. Now cabin heater is shown at the bottom. It has a process coil easily drainable, two-phase flow problems are less severe, can accommodate side end firing leading to floor being nearer to ground, and cheaper in smaller sizes. So these are the overview of the different types of heaters. Now I'll just show a water bath heater here. As you can see, these are the burners on the bottom, and then you have the hot flue gas duct going through the water bath and exiting through the chimney, and inside you have the process fluid is on the other side. So these are water bath heater. Now draft. Now draft is very important in a fire heater. Draft is basically a negative pressure which is kept inside the entire fire heater. Now why it is kept negative? There are 2 reasons for this. The first reason is the casing of the fire heater is always made from construction steel to keep the cost down. Now suppose the inside of the fire heater is kept at a positive pressure. So there are 2 things here. Suppose the casing has a leak. That means the flame is going to come out of that leak in the outside at a very hot temperature, maybe 700-750 degrees centigrade. If a person is standing there, he is going to expire there on the spot. Second is, if it's a pressurized inside the firebox, the gases are going to permeate through the refractory and go to the casing, which is, as I said, construction grade steel, and it is going to cause corrosion there. This is not good because then again you have negative aspect there. So that is why the draft is always negative inside the firebox and fire heater. The absolute pressure is negative as compared to atmospheric pressure. So any leak occurs, gas will go inside always, air will go inside. So here if you see the radiant section, the shield tubes is written. So that is called the radiant arc. That is where you measure the draft of the entire fire heater and control it accordingly. So here are based on draft, you have 4 types of draft. Natural draft system on the left. Okay, because of the hot gas, flue gas buoyancy, it is creating a draft inside the fire heater. This is basically a low efficiency, and you don't use this for very large heaters. You have the ID fan, induced draft system, where the ID fan is there. Then you have the forced draft system and balanced draft system. For very large heaters, balanced draft gives the maximum efficiency. Typical sections of a natural fire gas. So you see the radiant section at the bottom. Above that, you have the draft gauge is there and the radiant arc. The crossover is there. The shield section, as I mentioned, 3 bottom rows of the convection section are unfinned, called shield tubes. Convection section, and then finally the damper. This is a natural draft heater, of course. IDFD fan is not there. Now I want to show you on the typical heat distribution in a fire heater. So here you will see a fire heater which doesn't have an air preheater, APH. So if you can see, the radiant section is about 60%. Okay. So 60% efficiency is obtained in the radiant section. So if you don't have convection section or APH, you will get only 60% efficiency. If you add the convection section, you get 25% more, which is 85%. You still lose 15% energy. Okay. Now, if you add a APH, you are gaining that 5%. So you get 90% efficiency of the overall heater. Nowadays, heaters can go up to 93% also, depending on the vendor. But a balanced draft heater will give you 90% where the APH is there. Now, there are different process datasheet preparation. These are the various things a process datasheet process engineer has to inbuilt into the process datasheet. So I'll not go through each and every one. I'll be covering this in considerable depth in the advanced course also. Now, heat exchangers. So now there are many types of heat exchangers. Again, I'll be covering these in depth in my main advanced course. Presently, we are going to concentrate in this introductory webinar on shell and tube and air-cooled heat exchangers. But as one can see, there are many types of heat exchangers. Each has a specialized area of operation, and it is not that this is better than that. You cannot quantify like that. Okay, like air fin vaporizers at the bottom. These are very useful for liquid storages of oxygen, nitrogen. Air fin vaporizers are predominantly used there. But in our oil and gas industry, in the chemical plants, normally shell and tubes occupy 85%, plate and frame, and air-cooled exchangers are also there. Now, shell and tube heat exchanger we are going to cover now. So, shell and tube heat exchangers account for over 85% of new exchangers. Now, there are many reasons for this. So, it can be designed for almost any duty with a wide range of temperatures, pressures. It can be built in many materials. Many fabricators and suppliers are there. So you don't have a scarcity, and a lot of bargaining can be done. You can get the equipment at a cheaper rate, competitive rate. Repair can be done by non-specialists, and design methods and mechanical cores have been established for many years of experience. You have good softwares in the industry. HTRI is the premium software for design of this, and it gives an excellent design. It directly gives a TEMA datasheet also as an output. Scope of shell and tube. So maximum pressure, temperature range has been specified here. You can exceed this also depending on the specific requirements, but these are the normal ranges one can comply with. TEMA classification. So there are 3 TEMA classifications. TEMA is basically Tubular Exchanger Manufacturers Association. So class R is for refinery services. These are very stringent. Class C is for general process application. For example, you may have let's say a compressor having a lube oil cooler. So there you can go with a class C. Class B is for general chemical process services. Okay. So class R is the most stringent among these. Now exchanger types. So this is the demarcation as per TEMA. Now this is very important for a process engineer. Normally process engineer is the fundamental person who specifies the exchanger, the type of exchanger based on the requirement of the process. So he has to understand this in details. Plus the thermal design also process engineer does. That's why this is very important. So on the left you see the front end is there. A, B, C, N and D type. Shell types, I'll be explaining this also in the next slide. E, F, G, H, J, K, and X type. Okay. And the rear head types are there. So L and M basically are replicating the left A and B. So L is equivalent to A, M is equivalent to B type. But then you have other types like S and T, which are internal floating heads. So these are very important where you are cleaning of the tubes, outside of the tubes. And the U-tube bundle also can be pulled out for cleaning. But for the internal cleaning of tubes, U is not recommended because of the U bed basically. So different parts of a shell and tube exchangers, just for information. Many parts are there. There is a fixed tube sheet type as shown here. On the left, you see an expansion bellow on the shell side. Okay, this is used for thermal expansion. One has to be careful with the expansion bellow. I have seen consultancy specify expansion bellow for a large temperature differential heat exchanger, and the expansion bellow failed. Luckily, no fatalities were caused. So if you have a very large temperature gradient across the exchangers, then you should not specify expansion bellow. It is better to go with the S type or T type or the U type. Shell types. Now these are the different shell types. The E type is basically most common configuration without phase change, 1-pass shell. F type is 2-pass shell with longitudinal baffle. Counter current flow is obtained. Baffle leakage problems, however, exist. G type is split flow, so lower pressure drop is obtained. H type is double split flow. Thermosiphon reboilers is the application. J type is divided flow. Flow can enter or exit via the single nozzle. Older reboiler designs have the J type. X type is the cross flow type. X type, you have the lowest pressure drops in this. So we had used X type, for example, in a SRU plant, sulfur recovery unit, for the reheaters before the converters. So the pressure drop was very less. And the X type, basically, it is not a long exchanger, it is a box type exchanger. Because you don't have much play on the flow going through, so it becomes a box type exchanger. And the kettle type not shown here, but the kettle type reboiler is a phase separation integral to the exchanger. So we'll see it in the reboilers as we go forward. Shell side flow is shown, as one can see, just for information. So it's a horizontal baffle. The shell side flow is going, and the tube side flow is also shown here. 2-pass exchanger on the tube side. Construction of shell and tube heat exchanger. As you can see, the bundles of tubes in a cylindrical shell. Baffles are used to support the tubes. Gaps or clearances must be left amongst the tubes and the inside of the shell, in between the baffle and tubes, etc., for proper construction. And tube layouts. Now, as one can see, you have the different tube layouts. These are very important from a process engineer's perspective. He is the best person who knows the type of fluid. So triangle 30 degree angle, this will give you the smallest shell ID. More tubes can be packed, but cleanability is an issue. Okay. Rotated triangle 60 degrees optimization from pressure drop perspective. The 90 degree square and the rotated square are the best for cleanability services. So you can have a tube on a 1.25 inch, 1 inch tube on 1.25 inch pitch, or a 19 mm tube on a 25 mm pitch. Then the next slide. So the number of tubes. So this is a typical tube layout as given by HTRI, for example. Okay. So there is a 6-pass exchanger on the tube side. 1, 2, 3, 4, 5, 6 at the bottom. You can see these are the typical tube layouts. So number of tubes depends on fluid flow rates, available pressure drop. So number of tubes is selected so that the tube side velocity is between 0.9 and 2.4. Okay. Lower velocity to limit fouling, while upper velocity to limit erosion. And the shell side velocity is about 0.6 to 1.5 is maintained. So normally number of tube passes are 1 to 10. You don't want too many above that because you'll have the pass partition leakage will occur through the steam basically. Heat transfer will be reduced. Always remember shell and tube exchangers and air-cooled exchangers, the turbulence is very important because that contributes to better heat transfer. Tube pitch. So again, the tube pitch I've shown, triangular tube pitch, and the right side you see the tube pitch. Normally tube pitch is kept at 1.25 times to 1.5 times. So the of the outside diameter. So 1.25 to 1.5 is the range of the tube pitch. Shell and tube passes. So this exchanger is shown as single shell pass and 2 tube passes. So shell pass usually this is 1 in E. E-type exchangers, one shell pass, can be 2 in the F types. Tube pass always from 1 to 10. You do odd numbers have more complicated mechanical stresses, so are not chosen. Tube passes increase is done to increase tube side velocity for more turbulence and lower fouling. However, we need to see the pressure drop, which increases also. Okay. Then the tube outside diameter, as you can see, the D is the tube outside diameter and PT is the pitch. So the normal tube ODs are 15.88 mm, 19.04 mm, which is 3/4 inch, and 25.4 mm. Smaller tubes give more turbulence, but then cleanability is an issue. Larger tubes in critical services like a sulfur condenser in a SRU. There I have seen 50 mm tubes ODs, 50 mm tubes, but they are used specifically for cleaning services. So we'll go to the tube length. Now, as can be seen, tube length is shown as LT on the top. Okay. Baffle spacing is shown as B in the middle, if you see. And the baffle cut is shown. Okay. These are horizontal baffle cut is shown here basically. So tube length basically affects cost of heat exchanger. Longer tube length, smaller diameter of exchanger, and fewer tubes. Typically, tubes are 8, 12, 15, 20 feet length. Okay. For mechanical cleaning, maximum 20 feet tube length. Maximum possible is still 40 feet. But you have to be careful because transportation and all you have to also look at. Thumb rule is shell diameter to tube length is 1/5 to 1/15. Okay, this is a thumb rule basically. Maximum transportation length is 30 meters. Then your tube bundle removal in shell and tube types. The layout may dictate tube length also. So normally when you have a bundle removal, the piping person plans a vacant space where the bundle has to be removed. So if you have a fantastic tube length, you have to keep a fantastic space for the tube bundle removal. So that's why there also you have to compromise a little bit. Smaller tube length, less space kept for tube bundle removal. The process engineer has to interact for this while they are doing the thermal design. Type of baffle. Single segmental are mostly used. Double segmental is possible. Triple segmental. At the bottom you see NTIW, no tubes in window segmental baffles. These are used wherever you have vibration problems during the thermal designs. You can go for NTIW to reduce the vibration. On the right, you see rod baffle. Rod baffles are patented by Phillips Petroleum. These are good for very low pressure drop, high viscosity services. Many other proprietary designs are there, like Holtec similarly designed a nest type baffle. Spiral baffle is there, donut baffles are there. But 90% you probably will go with a segmental baffles, or at best a NTIW, which is for vibrational problems. Baffle cut. A baffle cut we will come to is normally kept around 15 to 45% maximum, with 20 to 25 being the optimum. Okay. Horizontal cut baffle is normally kept for single phase fluids, and for condensing phase fluids where you have two phase flow, always you keep vertical baffle cuts. So on the left you see vertical baffle cut. At the bottom is a small cut for drainage liquid. On the right hand side, horizontal baffle cut and small V notch for liquid draining. Now fluid allocation. This has to be done by the process engineer. It's very important. The tube side is preferred under these circumstances. Fluids which are prone to foul because you can clean them very easily. Corrosive fluids best in tubes because your tubes will be cheaper. The shell side material is not affected. Then toxic fluids to increase containment. Streams with low flow rates to obtain increased velocities and turbulence. High pressure streams. Then tubes are less expensive to build strong as compared to shell side, where very high pressure on shell side, it becomes difficult, costly exchanger. And streams which have a low allowable pressure drop. Viscous fluids normally go to shell side. So this is a fluid allocation thumbs up rule. Now reboilers. So there are different types of reboilers. We have vertical thermosiphon type as shown. This basically operates on the fluid delta P. On the left hand side, you have pure fluid, which has a higher density. Inside thermosiphon, you may be having around 20-25% vaporization. So that outlet pipe has two-phase flow, delta P reduces. So that is the driving force in the thermosiphon action. This is a horizontal thermosiphon type. This is a forced circulation reboiler. It's nothing but a shell and tube. Now, at the outlet, you will have two-phase flow again, but the pump ensures that you have very good circulation. Then kettle reboilers. So here you see a kettle reboiler, full vaporization is occurring, and the lean fluid is going from the bottom. So this is used in, for example, amine regeneration unit, where you have the amine from the regenerator bottom comes to the kettle reboiler. The water is boiled up, and the lean amine goes out from the bottom for the amine absorber again. Kettle reboiler again is shown. This is a trap out kettle because at the earlier slide you saw the bottom is going from the bottom of the column. Here from the sump, the draw out sump, the liquid is going into the kettle, and from the kettle it goes back to the distillation. So this basically acts like a stage, okay, theoretical stage in distillation. Internal pool stabbing type. This is normally not used because if any leakage is there, you end up in a lot of problem there. But it can be used in very small columns. Shell and tube exchanger, process data sheet. These are the things are required for thermal design of shell and tube heat exchangers. A lot of items are there to be specified by process engineer. Air-cooled heat exchangers. Now these air-cooled heat exchangers again, unlike shell and tube where the thermal design is done, in air-cooled heat exchanger, the thermal design can be done by process engineer. But here there are two things involved. One is the heat transfer area. Other is the fan operating power. So basically you also have an OPEX factor here, operating expenses. Not only CAPEX, you have OPEX also involved. So it is best left to the OEM to decide the thermal design of the large air-cooled heat exchangers. Okay. Shell and tube exchanger is a different matter, procurement point of view. Air-cooled heat exchangers procurement point of view, best left to OEM to design. However, for feed type jobs, you can do it in-house. For the actual detail engineering where procurement is involved, normally the OEM supplies the air-cooled heat exchangers. So he takes the guarantee for the fan power, etc., and the OPEX cost. Now, air-cooled exchangers are normally used where the process system generates heat, which must be removed. Now, air-cooled exchangers, they save on the cooling water, for example. Shell and tube exchangers, you require cooling water, where cooling water makeup is required in the cooling tower. So for, let's say, places where you have a desert, or for Gulf countries where you don't have that much water available, air-cooled exchangers work nicely. However, you have a limitation on the outlet process temperature. So with the cooling water, I can get 40 degrees centigrade. Air-cooled exchanger, I cannot get 40 degrees centigrade. At best, maybe you get 55 degrees centigrade on the process outlet. So here it is how it operates. So hot process fluid entering, air is entering from bottom, warm air goes out, cool fluid goes out on the right. So construction of ACHE. So code followed is API 661, ASME section 8 division 1, since it's a pressurized on the header side, tube headers. So last oil and gas HEAC are designed as per API. See, you can have small ACHE also. For example, our car radiator, that's nothing but an air-cooled heat exchanger. Okay, but that doesn't have to be as per API. It is a manufacturer standard. So like that, you have small ACHE also. For example, air compressor supplying plant air, instrument air. They have an air-cooled exchanger. You don't want that as per API 661. That's very costly. You can go with manufacturer standard there. Design software used is HTRI, HTFS. Okay, so these are the different things. Now, one important thing here, the bottom line I just mentioned, the whole assembly is usually mounted on legs or on a pipe rack. So this is very important for an air-cooled heat exchanger. Normally, the plant basically is a box unit. In the central is kept the pipe rack, on which the air-cooled heat exchangers are mounted, let's say at 6 meter elevation. This ensures that the air pickup doesn't have dirt and dust from the ground. Plus, the outlet hot air is vented to a sufficient high location so that you don't have it going and striking some operator somewhere. It minimizes on the area also. Okay, so the air-cooled heat exchangers located on pipe rack are very good, and they save on plot area also. Now, advantages are, these are the various advantages as I mentioned. So point number 5, you see, can save on plot area space by locating. Then only the OPEX is involved. You are saving on water resources and all. And then it saves on the cooling water system totally if you go with air cooled. But the disadvantages are, they are higher capex. OPEX cost also comes into play because of operating power of the motors. Tube rupture case, you can have a lot of hazard there, unlike a shell and tube. And winterization, you have to be careful here. Right? So in winterization, you don't want icing on the tubes. So you are in winter, in cold countries, the hot air is recycled back to the suction in certain proportion so that you don't have icing on the tubes. Types of air-cooled exchangers: induced draft, where the fan is on the top, tube bundle is below. Forced draft, fan is on the bottom, tube bundle is on top. So controlling ACHEs. So as you see in the middle, there are 5 methods: manually operated louvers, manually adjustable pitch (MAP), where you have to stop the air-cooled exchangers in order to adjust the pitch. Then you have the pneumatically actuated automatic variable pitch (AVP) fans, what are called. So here you have a volume booster bottom. Instrument air is used. Online adjust the pitch. Okay. Then the variable frequency fan drive (VFD). It's very popular nowadays for large fans, large ACHE, to give 50% on VFDs, so that in winter times also you need not drastically subcool. You can save on power also. And ACHE bypass controller. So these are the different methods used. Now process data sheet, again ACHE. These are the things required for thermal design of ACHE. Now distillation. So distillation, now mass transfer operations. So distillation is used in typical gas liquid contacting operations, including distillation, absorption, stripping, leaching, and dehumidification. Distillation and absorption are two most widely used mass transfer processes in chemical industry. Now please remember, a distillation is very efficient operation, giving very high purities. It is also a highly intensive energy consumer. Okay, so please remember that. However, crystallization and all, there's another factor involved with the solvent recovery and all these things. So always for large plants where you have reliability and maintainability, availability is important, one opts for the distillation system to reduce the complexity of the plant. So it relies on the boiling point difference, relative volatility, what is called. So absorption, again, there are some examples I have given here of the absorption, types of absorption. Now the boiling point diagram. So as you can see, the boiling point diagram shows how the equilibrium compositions of a component in liquid mixture vary with temperature at a fluid pressure. So the upper curve in the diagram is called the dew point curve, as you can see, while the lower curve is the bubble point curve. The dew point is the temperature at which saturated vapor starts to condense. Okay. Bubble point is temperature at which the liquid starts to boil. The liquid above the dew point curve shows the equilibrium composition of the superheated vapor. So the superheated vapor is on the top and the subcooled liquid is at the bottom. So this is called the boiling point diagram. Now a typical distillation assembly, as I have shown here, your feed is entering in the column. You have trays in the column. Top is called the rectification enriching section. You have the condenser. Reflux drum is there. Usually a pump is there at the bottom, not shown here in the diagram. Reflux goes into the column. Distillate goes out. Bottom portion is the stripping section. From the bottom, you have the, let's say, kettle type reboiler is shown, where heat in, heat out is going. And then bottoms is going out from the reboiler. So this is a typical distillation system, basically. Now here we'll go into the next slide. So a few distillation terminologies I've just put here. So one can see on the photo shown, the downcomer is there, the seal tray is there, active area is shown, liquid flow path is shown, calming zone, downcomer apron is shown, the plate below. This is a typical distillation. So there are some terminologies here. Active area is the deck area of the tray, which may either be perforated or fitted with valves or bubble caps. So it can be seal tray, valve tray, bubble caps. And is the area available for vapor liquid contacting. Calming zones, unperforated strips of plate at the inlet and outlet sides of the plate. Okay, as is shown here, basically. Downcomer is a vertical channel that connects a tray with the next tray. Okay. Then downcomer area is the area available for transport of liquid from one tray to the next tray below. Then you have the flooding. So this flooding is very important. First is the jet flooding. Jet flooding is due to massive entrainment of liquid to the tray above. Spray and of froth occupy the entire space between trays. So normally a column is designed for about a maximum 80% of the jet flooding. There are other floodings also which has to be checked for. Blow flooding, loss of liquid seal, downcomer velocity flood. Then you have downcomer weeping is there from the tray. Then you have this thing also, dump point is there, which is important also. So these are the various terminologies used when one has to design hydraulics of the distillation column. Now in the hydraulics, normally there are some free softwares available like Sulzor and Kordsgliss have their sites. Free demo software is there. You can practice all the hydraulics on that. Please remember, the person who supplies the tray, the OEM who supplies the tray, takes the guarantee for the hydraulic design. So your role is to check it. It is seldom that a process engineer designs the actual tray hydraulics, unless you are doing a revamp job in an operating plant where you may be called upon. Other than that, the OEM does the hydraulics and gives it because a guarantee is involved in this. The factors to be considered for design of a distillation column. So these are all the factors I listed down here. You can just go through that one by one. Then the other tray versus pack column. So one can see the different requirements of tray column versus pack column. Usually tray columns are used because for large oil and gas services, you have very large distillation columns because of the capacities. So tray columns are used. Pack columns are, however, used for specific services for clean fluids where you have very low delta P's. Let's say vacuum services are there, or very small columns are there where you use pack columns. Okay, the pack columns have their own field. Tray columns have their own field. So both are have different areas of operation basically. Again, the tray column can be used for dirty service. Pack column cannot be used for dirty service. Okay, so certain pros and cons are there for each type. Typical tray is shown here. This is a 2-pass. As you can see, middle is the downcomer for this particular tray. On the left and right are the other downcomers, and the flow path is going from the left is going towards the middle, from the right is going towards the middle. It's a 2-pass tray basically. There are other pass trays also, 1-pass, 2-pass, 2-pass center downcomer, 4-pass trays. Odd number of passes are not normally taken. The number of passes is chosen depending on the maximum flow path length. So that determines your number of passes to be taken. Type of trays. Now seal tray is the cheapest, but the turn down is only 50%. Below that it starts weeping. Bubble cap tray is the costliest. 40 years back, there were only bubble cap trays. After that, the valve and seal came into prominence. Bubble cap can give you up to 10% turndown. The valve trays are vendor proprietary design. Each vendor has his own design. Turndown normally is up to 25%. For special trays, for very small columns, you can have cartridge type trays. So they are exactly like our tiffin box. If you see, we have a tiffin box which you open and then you pull out that tiffin. That is how the cartridge tray is operating. It is not good. It's costly also. For very small columns, it's better to go with a packed column. Licensor trays are also there, like for example, Ripple, Baffle, UOP, high capacity. Sieve tray, how it works basically. So on the top is the normal operation. Okay, no weeping occurring. At the bottom, you see the low vapor condition has occurred, weeping has started. If the vapor is very high, again you will have the jet flooding. Okay. Bubble and valve cap trays are shown here, typical. Tray spacing, normally 600 mm is kept for large columns so that you can access the trays. For very small columns, you can have up to 450 mm 450 mm tray spacing. Because let's say 900 mm column, the operator can open the manhole and access the other side also. So 450 can be kept. That is the tray spacing. This is very important for the column design also. The tray design. So the following process inputs are required for tray design by the OEM. So as one can see, the vapor flow rates are there, properties are there, turndown requirements, system factor, that is the foaming tendency is important, design pressure, design temperature, operating conditions, material of construction, allowable tray pressure drop. These are the things which are required for tray design by the OEM. Tray design parameters. So these are the tray design parameters as required in hydraulic calculations. Column diameter, inside diameter. Many correlations are there for column diameters also. You have the Kister and Haas correlation. You have the Fair correlation. Souders and Brown correlation is there, which I'll just elaborate upon. Then you have the distillation column hydraulics. So step-by-step hydraulics are summarized at bottom. Okay, how it is done basically. So normally these are done by the tray vendor supplier, and they will give it to the process engineer in either the operating company or the engineering consultancy firm for checking and validating. Distillation column diameter estimation. Now here I have given a GPSA method called the Souder and Brown equation. There are other equations also, like as I mentioned, Kister and Haas is there, Fair correlation is there. So this is how the diameter is estimated basically. It's a rough estimation and to be formed up during the detailed hydraulic calculations. Hydraulic design, again, following parameters can be manipulated to provide a suitable hydraulic design. So here you see tray spacing, then downcomer width, all of these things you can play around with to get the optimum hydraulic design. There are certain guidelines available which I will not go into right now. I'll be covering that in the detailed advanced course on chemical process engineering. But these are the parameters. Tray stability diagram. This is very important. Here you can see. So here you can see. Here you can see the liquid flow rate is there and the vapor flow rate is there. So the good area is the area of satisfactory operation. So that is where the liquid and vapor flow rates are in good quantum. When the liquid flow rate is high but the vapor flow rate drops, you end up into weeping and dumping mode. Where the liquid flow rate is on the lower side and vapor flow rate is very high, you end up into entrainment flooding and excessive entrainment. So your area of satisfactory operation is where you need to normally operate at. Now we'll just go into the next slide. So the key hydraulic limits. So here the key hydraulic limits are listed here. These are the listed below for tray dry pressure drop, tray hydrostatic head, overall pressure drop, jet flooding, wear loading. So these are the hydraulic limits as I mentioned. Each and every has a hydraulic limit. Like for example, jet flooding, you have an upper of 80%. You don't go above that. Normally you operate, you design your column around 75%. A tray dry pressure drop, wet pressure drop also has certain limits. You don't want the excessive pressure drop across the column for design. That has its negatives also. Okay, so these are all required for the hydraulic tray design basically. Now here I have again mentioned what is important for a process engineer to understand. So here you see there are two separate guarantees involved in the tray column design. The first is the process separation guarantee, which is taken by the designer or the licensor, let's say. So now the designer who has carried out the separation in, let's say, Aspen Hysys package. So he has sized the column, he has found out the number of theoretical trays required to get the separation efficiency at the top and the bottom. So my product purity at the top, product purity at the bottom. These he establishes, number of theoretical trays has been fixed up. This is called the process separation guarantee. So this is normally taken by the person who designs the column process point of view. Okay. Second is the hydraulic guarantee. This is taken by the tray vendor. So the tray vendor who is actually supplying the trays will take the hydraulic guarantee. So he will design his tray hydraulics, let's say outlet wear height, downcomer width, downcomer design, flow path length, all this guarantee he will take. Okay. So please remember this. This is very important. Now pack towers and packings. So the pack towers we'll just go through now. So here you have different things are there. You have a distributor at the top. Many types of distributors are there. We are going to cover this in detail in the advanced course also. Packing supports are there. Liquid collectors are there. And finally, the vapor inlet devices, which can be a Chopin toter, it can be there. It can be a vane pack. It can be a symbol tangential entry can be there. So in this now, what is important is the pack bed height. Now, how to calculate that also we'll come to. But there's a certain limitation on the pack bed height also. So if you want a pack bed of 15 meters, you cannot have 15 meters in a single bed. The maximum height allowed is around 4 meters. So that means you have to break it into, let's say, 4 beds. So each bed has to have a distributor and a collector and redistributor. So all these things have to be planned by the process engineer along with the vendors. Packing types. The first generation packings are shown here: Rashik, Lessing, Pearl saddles. Second generation packings are shown: interlock saddle, Pearl ring. The third generation packings are what are now normally used. So IMTP is a very good packing, interlocks, metal tower packing. Okay, so we'll come to this. So packing types: Rashik, Lessing, Pearl saddle, the first generation, second generation, and then you see the third generation on the right, IMTP, which gives very large surface area for contact between the two fluids. Pack column design. The first step is, of course, to design the number of theoretical trays. So this is exactly like a tray tower. You do the process simulation. You can do hand calculation, but nowadays simulators like Aspen Hysys and all are used. And if it's a large project where licensor is involved, licensor will normally do this. So first step, there's no difference between the two types. Second type is estimating the HETP, which is height equivalent to theoretical tray. So depending on the type of packing, the HETP is already available. So for example, if you want Paul rings, so the HETP is available in literature. I'll show you in the next slide. Then IMTP, you have to is also available. Structured packing, if you are having, then you have to rely on the OEM of the structured packing. These are proprietary structured packing, and the OEM will give you the HETP for that particular structured packing. Structured packing should never be used where you have fouling services. Please remember that. Because it is very difficult to remove a structured packing. It's a very nuisance value if you have choking of occurring of structured packing. So this second step is when you have the HETP, then you multiply by number of trays to get total height H. Okay. Now I've given a brief table. So let's say distillation packing size is 1 inch. HETP is approximately this. Okay. Again, depends on the type of packing. But this is just a rough guideline I'm giving. Vacuum distillation again, packing size, and HETP. So the third step is designing the tower, estimate tower diameter based on hydraulics. So this is the third step. So you basically have this generalized correlation chart, and you have the on the each line of the graph is marked with an acceptable pressure drop. So these are the pressure drops. Okay, inch water column per foot of packing. So numbers in parentheses are mm water per meter of packing. So using this, you have the left hand side. You can get the value. On the x-axis, you already know the value. L by V, liquid and the vapor load, and the rho V by rho L is the liquid and vapor and liquid density. So you get the G from this. Once you get the G, you can estimate the diameter of the column. These are the pressure drops available normally as a thumb rule people use in the industry. So as you can see, it's very important. Now please remember this. Here you see vacuum distillation. See, the pressure drop is very less. Okay. Whereas atmospheric pressure distillation, you have a higher pressure drop. So vacuum service always pressure drops are very less because you don't have too much margins there. And for pressure distillation, you can afford higher pressure drops. Okay. Maximum any other system is 1 inch water per foot of packing pressure drop. The sequencing of column. This is important for process engineer, where you have many products which you have to separate out. Let's say you have from a LNG plant, you have a distillation train. So first column will be your demethanizer, followed by depropanizer, debutanizer. So this is the sequencing basically of the columns. So that is what I'm talking about here. So first, good engineering practices, first get rid of the troublesome components, which are the inert gases. Okay. Second is you always like wherever you have difficult separations, like which are having very low boiling points, those you take always at the last. So the difficult separation should be at the last. Okay. And always favor the direct sequence. Why the direct sequence? I'll explain in the next slide. So the next slide we'll go to is the sequence. So here you see 1, 2, 3 is the direct sequence. You are removing 1, 2 and 3 are going in the liquid phase to the next column. So your consumption of energy is less because you are only removing 1 here. Okay. In the next column, 2 and 3 are removed. Whereas in the indirect sequence, heaviest first. So here 1 and 2, you are boiling 1 and 2. So more energy is consumed. And then you are again 1 and 2 is being separated here. So this is the direct versus indirect sequence, the advanced course. Okay, we'll start with the separators category now. So let's start with the separators. Now separators basically are predominant in the industry. For example, you may have a amine regeneration unit, for example, in a refinery. So you have an inlet separator, which is a 3-phase separator. So you will have basically gas coming in, which contains H2S. Then you will have amine is there, and you may have some organics also. So 3-phase separation is required. Similar to that, you have let's say central processing facility, which is called a CPF, which is collecting crude oil coming from many different wells. So this has a separator at the inlet. Again, it's a 3-phase separator, separating the gas from the oil and the water. And a distillation column, let's say top reflux drum. This is also a separator because it separates the gases from the distillate. Okay. So as can be seen, that there are many reasons for separation. Now the vessel code. This is coming under pressure vessel code. So all separators will fall under pressure vessel code. In India, basically we use the American ASME Section 8 Division 1. Now separators use following methods for separation. One is the momentum. So in the incoming pipe, you can have an elbow, for example. You can have an elbow against the wall. So the elbow basically splashes the liquid against the wall of the separator, breaks the momentum, and creates separation for the gas and the liquid. Or you can have a cyclone, for example, which are vendor specialized items, which also give good separation. Then the second phase is the gravity settling. This is important. So in the gravity settling, using the Stokes law, the gas and the liquid separate out. I'll be showing you the formula in the next slides also. So the gas and the liquid separate out, and they are given enough residence time so that the complete separation occurs. Where you have 3-phase separation, you have a light liquid, heavy liquid also. So based on the rising velocity and the settling velocity, enough residence time is given, so the separation occurs very nicely. The gravity settling is there, second method. The third method is coalescing. Now the coalescer is a very specialized field, and this is an OEM item basically. So there are original equipment manufacturers who give coalescer blankets. The coalescing basically gives more area for promotion of the droplet sizes. So if a small droplet is there, it will coalesce. Coalesce means coming together. It will coalesce and become smaller droplets. So because of the large droplet size, separation becomes much faster. So the vessels which have coalescing media in it, they are basically smaller in size. However, you have to involve the vendor, and the vendor cost also has to be added to the vessel basically. So the separator types again. Now, depending on the gas to oil ratio, what is called GOR. Now, if the gas to oil ratio is very large, So suppose your oil is less than 15%, normally it is normal practice to go with a vertical type, which is shown at the bottom. So this vertical type you can see in, let's say, compressor inlet suction KOD. You'll have a vertical this thing. Then, for example, you have a plant air receiver as well as dry air receivers in compressed air service, which are always vertical vessels. So the reason is the liquid is much less than the gas, and that's why the holdup of liquid is very less, and gas goes out from the top. Now, wherever your oil is considerably more than the gas, let's say oil is more than 15% as a thumb rule, then you go with the horizontal type. So this horizontal type predominates in the industry. All the inlet separators you will see are always horizontal vessels, including reflux drum also you will see as a horizontal vessel only. So next slide, here we see the sizing method for two-phase separators. There are two types of method, the K value method and the drag coefficient method. So K value method is a method I have shown here, which uses the Souders-Brown equation. This is the equation, and this is the formula for that. Okay. Now K values are available in my book also. I have given the K values without demister, with demister, the different K values are there. Now the drag coefficient method in the next slide I'm going to show is specifically used for flare KOD drums, where you cannot have a demister. A flare system you cannot have a demister because of the choking tendency. So there you always use drag coefficient method. So we go to the next slide where the drag coefficient method is used. These are the formulas used. You have to define, here you can define the particle size also. The dP you see in the formula. So that dP is a particle size basically. Then the diameter calculation. So this is how you calculate the diameter for two-phase separators. Three-phase separator diameter calculations are a little bit more cumbersome. I'll not be covering that. In the advanced course, I'll be covering it. But for the vertical vessel, this is the diameter. VA is the allowable velocity, as we saw in the earlier slide. This is the VA is equal to VT, is called the terminal velocity allowable. This is the VA basically. And for horizontal vessel, you have horizontal allowable velocity here, vertical allowable velocity, and then you have to adjust. The horizontal drum is calculated by first assuming a diameter, a high liquid level, and no mist eliminator. Then using the required liquid holdup volume, calculate a tangent to tangent length. The liquid level and tangent to tangent length are then adjusted to maintain a vertical velocity and horizontal velocity as defined above. So in my book, I have given the actual template also. So you don't have to do manual calculations. You can actually use the template and do these calculations. And many examples are given in my book also, for the which I'll be covering in the advanced course. The next slide is for three-phase separators. Now, three-phase separators, the thing is you have one gas phase and you have two liquid phases, light liquid and the heavy liquid. The configurations of the three-phase separators are many. For example, if you have a light liquid of very small quantity, you can go with a bucket and weir type three-phase separator, where the light liquid is collected in a bucket and then heavy liquid overflows through a weir at the bottom. Or for example, if the heavy liquid is of a lesser quantity, let's say water is there and the oil is of a major quantity, then you can have a boot type assembly at the bottom, because water is heavier than oil. It will collect in the boot and then it can be drained off. So there are many configurations possible. What is important here is liquid-liquid separation. So in liquid-liquid separation, you have three laws here depending on the Reynolds number. So everybody, all of us know the Reynolds number. So Reynolds number is specified here, dV rho by mu. Okay. So first you calculate dV rho by mu and then you see which law you fall into. So Stokes' law is NRE less than 1, intermediate law 1 less than NRE less than 1000, and Newton's law is 1000 less than NRE less than 200,000. So depending on this, different formulas are there, and you have to calculate the velocity and then do the diameter and the further sizing of the vessel. So inlets in separators are many types. Cyclones are there, Chopin-Toter is there. You can have an elbow type device also. Outlet gas can be a wire mesh vein pack type. Okay, wire mesh can be designed by the consultant. These are fairly enough data is available in the market. Vein pack are vendor proprietary items. You have to counteract with the vein pack. They are more efficient than wire mesh. But they can be used, for example, if you have some choking tendency, wire mesh can get choked. Vein pack is better to use. Boot arrangement is required. Partition plates, coalescers, vortex breakers, these are all internals. Process inputs required for separators. So all of these are the inputs required for the separators, as can be seen. Process engineer has to give these inputs. Now we go to pressure vessel category. So pressure vessel, any vessel in the industry which has vacuum or pressure in it categorizes into a pressure vessel category. So it can be many types. Processing may be reaction, fractionation, mixing, separation, surge volume, etc., etc. Okay. So we'll come to this. Now many types of standards are there in the industry. Each country has its own pressure vessel code. In India, we follow normally the BS standard. So BS 550 is followed. For example, you have a mounted bullet storing LPG, propane, or butane. BS 5500 is cheaper than ASME Section 8 Division 1. Okay. Normal pressure vessel, we always follow ASME code. So ASME Section 8 Division 1 or Division 2 is the normal pressure vessel code we follow. There are many types. Different countries have different codes. In France, you see the SNCT could have code. Okay. New Zealand has the AS NJS type code. India also has IS 2825, Indian Standard Code for unfired pressure vessels. Now, next slide is very interesting. This slide gives you for a vessel of the same size, the comparison of thickness using various pressure vessel code. This is from a very, very reputable company. And as you can see, the pressure with the PSI versus the wall thickness on the y-axis. So different codes have different wall thicknesses. The more the wall thickness, obviously the cost of the vessel also is going to go up. So the Germany AD Magblatter you see is on the lower side, and on the right hand side, New Zealand code is the maximum wall thickness. So our BS 5500 and ASME Section 8 is falling in the middle somewhere. Okay. So if you are have a project in Germany, obviously you will follow the AD Magblatter. But in India, no, even if it is cheaper, nobody is going to follow a German code because you are not going to get a manufacturer for that. So normally in India, you will follow the ASME code or the BS 5500, as I mentioned, which can be used for the mounted bullet categories. Okay, then process input required for pressure vessels. So these are the different inputs which a process engineer has to give for pressure vessels to the fabricator or the mechanical engineers also. Here you can see insulation requirements here at the J category. This also is very important. Process engineer has to decide the thickness of the insulation and give it to the mechanical engineers. So process engineer has a lot of work in any project and they are central to the team. Excuse me. Now we come to the storage tanks. Now storage tanks are many types. Atmospheric types are there. So these are atmospheric types. So these are generally ranging from small shop fabricated tanks to large field erected tanks, which are called in situ manufacturing at the site. Okay. So all the tanks which are very large, you see, they are always manufactured at site using the plates, erecting with the plates. Then you have low pressure category tanks, medium pressure category tanks are there, and high pressure category, which come into the spears, cylindrical bullets. For example, as I mentioned, LPG is stored in bullets, cylindrical bullets. If it is propane, you have a design pressure of 21 bars. If it is butane, you may have design pressure of around 15-16 bars. So these are the high pressure category vessels. Storage tank types. Now this is important. First is the fixed conical roof tank. This is always used for water services or for high boiling chemicals. Like if you have a fuel oil tank, you can have open gooseneck vent at the top, and since it is to be stored at, let's say, 100 degrees centigrade, you don't have flammability at the top, so you can keep an open gooseneck and you can keep a fixed conical roof tank. A dome roof tank is used, for example, if you are storing a material like pentane. So pentane has a low vapor pressure, so you cannot keep a gooseneck. You have to store it in a pentane dome roof tank, which has a dome roof basically, and so on and so forth. External floating roof tank is used in the crude oil services. I'll be covering this in brief in the next slide also. Refrigerated cryogenic storage tank. These are used for example, liquid ammonia, which is stored at -33 degrees centigrade. That is stored in a double-walled cryogenic storage tank. Same for cryogenic propane, cryogenic ethylene, cryogenic LNG. These are all stored in cryogenic storage tanks. Storage tank codes. So here you see API 620 and API 650 are there. So normally water tanks in oil and gas industry are as per API 650. And then most chemical tanks otherwise will follow into the API 620 category. Here you see example of the storage tank. So cone roof tanks, service examples I have given. So you can have like fuel oil tank, as I mentioned, is a cone roof tank. The high boiling fluids like kerosene, diesel, you can have a cone roof tank. Stock volatility is written on the right. A floating roof tank can be a crude oil storage. Why a floating roof for crude oil? Because you have low boilers in it. So the floating roof basically minimizes the loss of emission of the low boilers. Then spheroids are used, for example, light straight run naphtha and gasoline. High pressure spears are used for butane, for example. Nowadays, the hot tune spears are going out of fashion. People normally go with the mounted bullet, which is going to give you lesser safety distances in the plot plant. Firefighting requirements also are less. Okay. Then the utilities in CPI. Now here I'm going to elaborate on the utilities one by one. So I have covered this in extensive detail in the advanced courses, which is about 2.5 days I'm spending on the utilities. However, here I'll be giving you a brief overview. So first is the compressed air, plant air, instrument air system. Now any project requires plant air and instrument air. Plant air is used for general cleaning purposes. Instrument air is used for the actual on-off valves and the control valves actuators. So, the requirement is plant air can be saturated with moisture, that is okay. Instrument air has to be dry. The atmospheric dew point is normally minus 40 degrees centigrade, and you do not have any corrosion, etc. is not tolerated. Particles are not tolerated because the actuators may get choked and the control valve may not work properly. So the first is the filter. The filter is basically depending on the type of country you are in. Let's say you have in Saudi Arabia, if you are putting up a project, it's a desert country, you will normally have a dust filter, which is for desert application. So the filters are robust. So you have to specify this in the process data sheet. The compressors are there. For small applications, you can go with a recep type. Normally, the oil-free screw types are recommended. Why oil-free? Because oil is not acceptable. It may choke the air dryer, as well as it may go with the instrument air and choke the actuators downstream. A lot of places, however, oil type compressors also are used. In that case, if the client prefers, fine, no problem. You can have a oil filter at the outlet and make sure the oil specification is specified and the oil filter is procured for that oil specification only. Wet air receiver is planned. It's about 3 to 5 minutes storage. Air dryer is there. Air dryer is of many types again. You can have a heatless dryer. Each type has its own pros and cons. Heatless type is there. Heatless dryer is there for small capacities. You have an internally heated type dryer. Then you have a heat of compression type, HOC type, what is called. You have a no loss split flow type is there. Refrigerated type dryer is there. Blower reactivity type dryer is there. So each type dryer has a different application. Pros and cons are there. So that you have to choose properly as a process engineer. Then dry air receiver is there. This is very important. You have to store 15 minutes dry air. It is not mandatory, but it is good engineering practice. And the minimum dry air pressure, there's an alarm at the outlet of the dry air receiver, which gives a low pressure at 4 bar. So that 4 bar is minimum required because the actuator requires minimum 4 bar gauge. So that means if a normal instrument is being produced at 6 bar, then between 6 and 4, the dry air receiver has to store 15 minutes of consumption. Okay, that is a very good engineering practice. Now we come to the water systems. Water systems are very crucial. Any plant has to have some sort of water, and the different types of waters are there. Fire water is there. You have raw water is there. Potable water is there for safety showers, for drinking purposes. DM water is there for boiler, etc., as well as process use. So here you see raw water entering from the left. This raw water can be coming from many sources. For example, it can be municipality water. In let's say Gujarat, you have the GIDC supplies the water, Gujarat Industrial Development Corporations. You can have your own borewell supplying the raw water. In case you are in the desert area, let's say you don't have water scarcity, you have water scarcity. If you are nearby the shore in the Gulf countries, they have desalination plants. So seawater is converted to make raw water, and from there the raw water is taken. So raw water basically can directly go to fire water tank and fire water. This fire water system is done by the technical safety engineer. You just understand that it goes to the tank. Okay. Other than that, I'm not going to elaborate much more here. In the detailed advanced course, I'll be elaborating a little bit for the general knowledge of the process engineers also. The raw water tank you see on the left, from where the pump is there. So this goes to multiple users. First is the cooling tower as a makeup water. Okay. On the right, you see recycled water from ETP is also coming to cooling tower maker. Raw water can go to utility stations for floor washing, etc. You have it can go to the potable water system where you have a UV treatment. It's ultraviolet treatment. Alternatively, you can also dose sodium hypochlorite, NaOCl, which is also good for killing the bacteria so that the potable water doesn't have fungus or bacteria in it. This potable water is used for two purposes. One is safety showers and toilets. First is safety showers, second is the toilets in the buildings. So it is normally a closed circulation because safety showers is a safety device. It has to be in operation 24/7. So this pump always has emergency power also. Then DM water unit you see at the bottom. The DM water can be going to multiple users. It can go to plant, it can go to boiler as a boiler feed water also in the thermal deaerator. Now we go to the steam condensate system. So in the steam condensate system, as you can see, first the boiler is there, the hatched area. So from the boiler, the steam is going. Now a refinery may have all these three types of levels. One is the high pressure level 42 kg. Second is medium pressure, which is 10 kg. Third is the low pressure, which is 3.5 kg. So a refinery may have all three pressure levels. Other industries, it depends on the requirements. But this diagram gives you an overall concept. So the steam header is going in the high pressure steam. It goes to the main header. Pressure PC is controlling the steam boiler firing rate completely. This steam header can be taken through a condensing turbine, okay, and you can produce power, or you can take it to a PRDS assembly. On the right, you see desuperator taken to the next level of steam. From the next level, you can go to the heat exchangers, which are the actual end users from where condensate comes out. You can have a back pressure turbine to produce power also. You can have, again, you can have a PRDS assembly, what is called pressure reducing desuperating station, to go to the LP level. From LP level, again, you can go to heat exchangers, produce condensate. Condensate goes back to the flash vessel, condensate flash drum, and then back to the deaerator. This deaerator is a very important equipment. It separates the CO2 and the oxygen from the condensate so that the boiler doesn't see corrosion. You can also dose in this hydrogen, sodium sulfide, which are the oxygen scavengers. Okay, so this is as far as the steam circuit is concerned. Now, typical hot oil circuit. Now, hot oil is a thermic fluid system. So there are two types of thermic fluids. One is you can have a hot oil vapor, you can have a thermic fluid vapor. Other is you can have thermic fluid in liquid condition. Now, the vapor where it is used, I'll just inform you. Let's say you have a textile plant which is producing partially oriented yarn to extrusion in an extruder, and then through the spinneret, the POI yarn is produced. The melt line has to be kept at 280 to 90 degrees if it is, let's say, nylon 66, and it has to be kept at around 190, 195 if it is, let's say, polypropylene. So here now the melt line is very small because you don't want it very large. So the melt line is kept on the outside. The annulus is kept heated using Dowtham vapor. So Dowtham is a thermic fluid in vapor condition. So there is a Dowtham fluid vaporizer electrically operated at the ground floor. The vapor rises up like steam. It condenses on the melt line, comes back into the Dowtham vaporizer. So Dowtham A is used for nylon 66. It starts boiling at 257 degrees centigrade and it creates only 0.3 bar gauge pressure at around 290 to 95 degrees centigrade. Dowtham J is used for polypropylene because it starts boiling at around 180 degrees and around 195 it again creates about 0.3 bar. Why this Dowtham is used? Because you cannot have steam at that very high temperatures. The pressures of steam are so high that your melt line design will be so thick, you will not be able to engineer that properly. Now that's a vapor system. Now the liquid system. Liquid system, Dowtham, there are many types. You can have Thermalon 66 is there, for example, which is produced by Thermax. Like that, there are many companies producing hot oil. The hot oil basically does not boil. It can be used at very high temperatures, and that is the advantage of the hot oil. So here you can see the circuit basically. There's a hot oil heater is there on the right. Fuel is there for burning. The hot oil is going, the pump is there on the left of the heater, which pumps it through the hot oil heater out into the users. There's a bypass FCV kept. It goes back through all the users, back into the expansion tank, which is a blanket gas, nitrogen blanketing, or you can keep fuel gas blanketing also. And then finally, that's the expansion tank, and then goes back to the pumps. It's a circulating system basically. Okay. So this is as far as the hot oil system is kept. Expansion tank is kept because you may want to heat up the hot oil from ambient temperature. Let's say you have a Diwali shutdown. You have a Diwali shutdown of 10 days. Your hot oil has cooled to 40 degrees. You want to now heat it back to 300 degrees or 290 degrees. So that thermal expansion is a huge quantum. So that's why the expansion tank is kept. Next is the nitrogen system. So nitrogen system is very crucial. Nitrogen is an inert gas used in tank blanketing. You may have pipeline purging, vessel purging. So all these users are the users there for the nitrogen. So nitrogen is basically produced. The upstream part is similar to a plant air system. You have filter, compressors, plant air buffer is there. Then you have a nitrogen generation unit, which can be PSA, pressure swing absorption, or membrane based or cryogenic based. Cryogenic nitrogen is the best quality. However, cryogenic is very expensive, and they are only taken for very, very large capacities. Otherwise, PSA can be used, membrane can be used. There is an oxygen problem with PSA and membrane. So wherever you have oxygen limitation, you put a deoxo unit downstream of PSA or membrane. For the cryogenic, you do not need a deoxo. It is already quite high in purity. Then the gaseous nitrogen storage is there, and finally the users get the nitrogen. Now in nitrogen, you have to remember one thing which is very important. There is let's say you have a sudden thunderstorm, or you have a large maintenance shutdown requirement of nitrogen. So then this particular generation may be insufficient. So there is this is called peak demand of nitrogen. When let's say the thunderstorm, the large tank cools down drastically, or when you stop your production, you need large quantum of nitrogen for purging, etc. So people keep a demand supply on the backup. That backup can be of two types. You can have a liquid nitrogen along with a vaporizer, or you can tap this gaseous nitrogen from 6 bar, take it to a compressor, compress it to 30 bar, take it to a 30 bar storage, and from that 30 bar, whenever peak demand occurs, you take it back to the header for nitrogen. So that's how you cater to peak demand. Effluent systems. Now, effluent systems are very important. Nowadays, Pollution Board has got very, very strict on this, and it is very important. So here, if you see on the left, this entire plant is basically a ETP plant. First pit you have is a neutralization sump, where you have the first flush of rainfall coming. This first flush of rainfall is nothing but the first 15 minutes of rainfall. So when it this basically cleans the ground. So the ground may have some contaminations of oil, chemicals. So that first flush is taken to this tank, so that you don't directly divert it to storm water. After 15 minutes of rainfall, that rainfall can be diverted to storm sewer because it's clean water. Similar to that, process effluent comes in the left pit. This basically pit is kept for 12 hours storage, so that you can have some mixing and buffering of the effluent. You can have a homogenization of the effluent. Now from this starts the ETP plant. So you'll have primary treatment, which is nothing but multigrade filters, etc. So that you can clean the effluent from solid particles before it goes downstream for the secondary treatment. Secondary treatment is nothing but the biological treatment, where the bacteria is used, which basically decomposes the organics, etc. And that's how you clean up the effluent. So this again, the secondary treatment is a OEM item. It is not easy to design these biological treatments. Conventional biological reactors, the NBBR, which is there right now, these are very patented type of designs, and always one should go with the AEM there. Tertiary treatment is nothing but a polishing step. So you have activated carbon filter here, which basically polishes. This entire thing is a complete package item. Please remember that. At the outlet of the tertiary, you have a guard pond, which is nothing but a final guard bond. As indicated, it's a guard bond. So if there is any slippages, you can use this guard bond so that you don't send out any contaminated effluent out from your plant. Now, as you see on the top, the clean effluents, DM unit effluent, which is basically, let's say you have a resin-based DM plant, where you are using the strong acid cation, or you are using a strong base anion mixed bed unit. They have to be regenerated. So that is this effluent. It is neutralized there in a sump pit and then pumped to this guard pump. So that is clean effluent. Cooling tower blowdown is there, boiler blowdown. These are clean effluents. From here, basically, now this pump, you can decide. Now, suppose you have a permission from the pollution board that you can now send out this effluent, then fine. This effluent can be diverted directly out if it is meeting the effluent board limits, or if it is a ZLD plant, so zero liquid discharge. Now the pollution boards are insisting that new processes always have a ZLD. So zero liquid discharge if you have, then you have to pump it back to the ultrafiltration to a reverse osmosis, recover as much water. Then that water, the brine of the RO can be sent for evaporators. So MED, multi-effect evaporators are kept here. And finally, then the zero liquid discharge occurs. It's only the inert solids are taken for inert landfill. Okay. And the permeate, which is good quality water, is recycled for cooling tower makeup or gardening. The brine, again, you can send it out if you have permission. You can send it to a CETP. For example, our Vapi area has a CETP. So if they allow you, you can do that. So these are things one has to look for in the basis of design to freeze. Now the flare system. This is a very important system. It's a fundamental system and it is a safety system. The flare system has to be always on if your production is on. Okay. So here if you see, each and every vessel has a relief valve, or you may have a rupture disc. The flare header is there, which goes in a flare KOD drum, knockout drum. From there it goes to flare stack. The flare stack has the pilots. You also have a molecular seal at the flare riser so that you can avoid the oxygen air ingress back into the system. So molecular seals are of two types. You can have a molecular seal where you have the inversion occurring, or you have a velocity seal where velocity is an impediment for the reverse action of air into the flare header system. Also remember that this flare header is not shown here, but at the end of the flare, either nitrogen or fuel gas is kept continuously purged. Okay, so that oxygen ingress is prevented. So this is as far as flare system. There are pilots on the flare burners. These pilots have to be continuously operated. In large refineries, there are no issue, but in small plants, let's say you have a flare which is mandatorily required, they also have a LPG backup system. So that can supply as a backup to the flare pilots basically. Here we see a refrigerant schematic. So refrigeration is a simple schematic. Again, refrigeration are many types. You can have an ammonia vapor absorption system. You can have a lithium bromide vapor absorption system. Here I have shown the conventional system, which is basically you have a compressor. The refrigerant you are compressing, taking to a condenser where cooling water or air cooled it can be. Expansion device is there where you are throttling it. JT effect occurs, Joule-Thomson effect. Out goes because of JT effect, you are dropping in temperature, it goes to evaporator. Evaporator, you have the process fluid which is being refrigerated, and then our refrigerant gas evaporates, goes back to compressors. This is the refrigerant circuit basically. This is again a package item from the vendor. Typical chill water system. A brine system also can be same. Chill water is normally kept about 6 to 12 degrees supply and return temperature. A brine system normally has methanol, or you can have MEG, monoethylene glycol, as an antifreeze. So I have operated brine systems at minus 20 degree supply and about minus 8 to 10 degrees as the return temperature from the brine. So as you can see, the top is the cooling tower system. The middle you see the chiller, which is the package item. At the bottom is the chill water circuit. Now heavy fuel oil system. So as I was mentioning in the beginning and the pumps part, you have the fuel oil system. So the HFO pressurizing pump, you normally use screw pumps or gear pumps here. So the HFO tank is shown, heavy fuel oil. This has to be kept in heated condition because when you are firing in burners, viscosity is very important. 25 centi-stokes is the viscosity minimum acceptable for the burners. You have to keep it at 25 centi-stokes. So that's why the HFO system is kept at a minimum temperature, maybe 100 degrees, maybe 120 degrees, depending on the fuel oil. One has to keep the centi-stokes, and then you decide the temperature. So in the fuel oil tank, you will have steam heating also, although not shown here. Then the HFO pump is there. You have an outlet, there's a heater where you are putting, let's say, steam and condensate, so that you are heating this basically. Then you have strainers. Now this entire system, please take note in the diagram. It is continuously kept in circulation. So it is always kept pressurized. So normally you keep it around 10 bar pressure. when the burners are operating, they take the draw off from the 10 bar header. You take atomizing steam also to the burners. That atomizing steam is normally 12 bar, and then you have a 2 bar delta there, and then the burners are atomized, and the burners then operate in the fire heater. So they're very important. This system is very crucial in large plants. It's continuously kept in circulation. Now a typical fuel gas system. Now wherever you have fuel gas, you are firing in burners. This fuel gas may have condensations. For example, you have pentane, hexane. These type of fluids may condense out. So you don't want two-phase going into the burners. So in the burners, if you have two-phase going, that's not good. You'll have fireball occurring. You may damage the internal of the fire heater. So that's why a fuel gas system always has a KOD. So there's a knockout drum kept at the upstream. This from the outlet of this heater, always the fuel gas line is kept heat traced. Normally you use electric heat tracing to keep it at around 40-45 degrees centigrade, so that it goes in vapor stream even in winter conditions to the burners. And this is basically a typical fuel gas drum. Now the next is the cooling water system. So typical cooling tower is shown. There are many types of cooling towers depending on the capacity. So makeup water is shown here, level controlled on the basin of the cooling tower. Cooling tower pump is shown on the right. You have the users, and from the users by gravity, the return water is going back into the cooling tower. Now there is I've shown an auto valveless gravity filter, as you can see. That is nothing but a AVGF. This cooling tower, because it is operating by induction of air into the cooling tower using fans for the cooling, that is why a lot of dirt and dust comes into the system. So it is standard engineering practices that you have to put a filter. AVGF operates on the return header, so it doesn't use any energy. You can also have a pressure sand filter on the discharge of the pump, and then put the pressure sand filter discharge back into the tower basin. But this uses pump power, which is higher OPEX. So this AVGF capacity is kept roughly around 4% of the circulating cooling tower. Why 4%? See, if you multiply 4% by 24 hours a day, you get 96%. So what this means is that the entire circulation is passed through the AVGF one time per day, once per day. So you are assured that the entire circulation once per day has been cleaned, basically. Okay. Now there are other things in the cooling tower I'm going to take in the advanced course, which I'll not be elaborating now. Utility parameters. Now each utility has a certain parameter which has to go with the basis of design. So what are these parameters? Here you can see pressure, temperature, dew point, purity, viscosity. These are things you need to specify so that you can design the system accordingly, and the vendor can give the packages accordingly. So in the next slide, you see examples. Instrument air, normal pressure, minimum pressure 4 bar, temperature, atmospheric dew point, cooling water, what are the parameters? These are all parameters which are there for the different utilities you encounter in the package. Then the steps required by process engineer for identification of utility requirement. Now here you start from the left to the right, okay? So utility identification is what is in the center. On the right, you have the simulation report as an input, then process design basis as an input, process flow diagram, and finally HNMD. These all inputs go into the utility identification. And what are the outputs coming out from the process engineer? Again, you start from left to right. Utility parameters, utility concept note is made, how you are going to produce that utility. Utility equipment list and PDS is generated. Utility flow diagram is drawn, and finally utility PNID is drawn. So these are the various utility related parameters. Now process engineering documents. Now overall process engineering documents, as you see, are many in nature. These I have listed the entire gamut here. However, depends on the type of project you are doing. All may not be required here, basically. Okay. So this I'll be elaborating in detail as we go along. In chronological order, I have put them. First is the basis of design. Second is simulation report. The simulation report is done initially. You can use any software like Pro2 is there, Hysys is there, Promax is there. Now, I just want to clarify one thing here. A normal process engineer may spend maybe 10 to 15% of his time in using simulators. The rest 85% is spent doing all this documentation. Okay. So a lot of times I find junior engineers, they think every time they have to do 100% simulation. That is a wrong misconception. Maybe if you are working in a licensor office, where they have to do the simulation. There they have a core team who might be doing day in and day out simulation. Else, maybe 10%, 15% max you may be using a simulation. Okay. The rest of the time, all these other documents have to be deeply looked into. There was one engineer in my past when I was heading one process and loss pay as a HOD. He got very much dismayed when he found that he is not required to use simulation. But this should not happen. So please be careful. It's good to know simulation, but that is not the whole thing that you are doing as a process engineer. So after simulation comes the block flow diagram, PFD, HNMB, process philosophies. These are very important. Let's say the isolation philosophy, winterizing philosophy, sparing philosophy. Then you have the vent and depressurizing philosophies. All of these go as inputs to the PNID. Okay. So again, equipment list MSD, which is material selection diagram. This is produced by a metallurgical engineer and has given as an input to the process engineer. DPDT diagram is very important. I'll be explaining this also. So all these documents are, now we'll go into which document under which project is required. So for the utilities also, these are the various documents which are used for the utility. Many of these documents go in the part of overall document, like utility control narrative. There's one control narrative produced for the entire project. It includes utility also, for example. Line list, same thing. Now, BDEP documentation. Now, it is very important. A BDEP package is normally produced by a licensor. It is given to the client or engineering company. For example, UOP calls it the Schedule A package. So Schedule A, black books, what are called. So UOP Schedule A package is given to an engineering contractor who further carries out his engineering, whether it is feed engineering or whether it is detail engineering. Okay. So that's what I've elaborated here. The engineering company further carries out, depending on type of project award, feed engineering or residual process engineering and detail engineering. So the BDEP normally contains these following things. Now you see there are many documents which are not listed here, which our engineering contractor has to produce from the BDEP package. Okay. So the feed documentation, now feed is front-end engineering design. Basically, it takes about 5 to 7 months for a large size project. And a process engineer has to produce a lot of documents which are inputs to the other disciplines. So they can also do their engineering. And finally, the material takeoff is produced, which goes into cost estimation so that you get a plus minus 10% cost accuracy. Here you see in the end, heat exchanger thermal design. This is also there. Now, what is not here is pre-commissioning philosophy. Then you have the FAT participation, which is factory acceptance test. You have the operating and maintenance manual. These are not part of field documentation. Vendor document review is not on a part of the feed document because there is no procurement occurring in feed stage. Maybe you may procure LLI, long lead items, but that is a customer preference to minimize the further detail engineering step. However, 90% of feed jobs don't have LLI procurement. The feed engineering documentation goes in preparation of ITB, which is invitation to bid. So that invitation to bid is sent by the client to the market. From the market, he will get maybe EPCM quotes or EPC quotes, depending on his philosophy. Now, detail engineering documentation process. Now, all these I'm going to cover in vast detail in the advanced course. So presently, I'm just going to skip through. So as you can see, the additional to the feed, these are the documents which the engineer produces in the detail engineering stage. So here DCS graphics is there, pre-commissioning manual, operation maintenance manual. All of these are part of the things which are not there in the feed. Okay. Vendor document review, isometric check, all of model review 60%, 90%. These are all things in the detail engineering he takes care basically. Now in the BOD, basis of design, there are many things that are important. For example, design pressure. So here are just listed here the various pressure terms and the who is specified by. So here you see only one is specified by mechanical. All of them are specified by process in the basis of design. Then design pressure, again, different companies have different standards, but this is just one standard I am putting here. How you define in the DPDT also, how you define the design pressure, design temperature. This is design pressure, we'll go to design temperature. So again, design temperature in BOD, the temperature terms are there and who is specified by. On the right, everything is specified by process, as you can see. Then design temperature, how you specify. So suppose you have a process which is at 80 degrees centigrade. So you take a 10 degree excursion. So 10 degrees is 90 degrees is your maximum operating temperature. And then you add a 15 degree margin. So it becomes 105 degrees is the design temperature. provided there is no other alternative case which can go to a higher temperature. So that 80 degrees operating temperature, 105 is the design temperature. That's how it is. And for the cryogenic liquids, of course, you don't have to add so much. You can keep a minimum margin there for cryogenics. Design margins. Now this again is part of the BOD. So for example, here heat exchangers add 10% to duty and flow rate. So this is again standard. This is defined and frozen in the basis of design, and this goes in the implementation, and the execution accordingly has to be done. Same for the compressors, process vessels, pumps. Process flow diagram. So what is the process flow diagram? It's a very fundamental document. I'll be covering this in deep along with the inputs, outputs in the advanced course also. Each and every document I'll be covering there. But just for information, this is a fundamental document. It comes from the simulation report, and the licensor may prepare it, or if you are executing the entire project, the engineering contractor who is executing may prepare it. So process flow document represents basic information. So these are produced at very early stage after finalization of design basis. Okay. So it puts a finalization of scheme, calculations, including simulation, to be ready before start of preparation of PFDs. So what is there as information? All the major items are covered. All the streams are covered in bold, process streams. Utility streams are also shown. The process conditions are shown in this. The stream compositions are shown. Now, the stream composition you can also show in an alternate document, which is called the heat and material balance, HNMB. If the composition is very vast, suppose you have 15 constituents of that stream, you cannot show here. It has to be a separate HNMB document. Okay. So basic control loops are shown. And then package items are also shown here in PFD. Stream information on PFD, again, what is shown as stream information. So these are the various stream information. Now, next slide is also very important. What is not shown on PFD? This is important. So any piping items like valves, traps, stabilizers, these are not to be shown. Only basic control loops are shown. Local instruments are not to be shown here. No alarms, no totalizers. No field instrument to be shown. Dikes not to be shown. Drain line not to be shown. Minor pots and pans. For example, a storage tank has a vent seal. This is not to be shown. Okay. Then piping and instrument diagram. This is a very important document. It is a very dynamic document. Throughout the project life cycle, it is dynamic and it is updated on a routine basis. So P&I diagram is a fundamental document in which all disciplines carry out the further engineering. And the process engineer is the person responsible for this document. So it has many stages, well-defined stages. You will have IFR, which is issued for review, IFA issued for approval, IFH issued for HAZOP study, IFD issued for design. The field engineering ends at IFD, for example. IFC is issued for construction, and the as-built is finally at the as-built. I'll explain all this in the next slide. What are the inputs required? So these are the inputs required on the left for preparing our P&IDs. Okay. Now, as I mentioned, the different stages you can see here in the P&ID. So each stage has a particular definition. After IFD revision, you enter into management of change. So issued for design means frozen P&IDs. After that, any changes there, it has to be well documented and intimated to all stakeholders. Okay. Then the equipment list is another fundamental document. Process engineer generates this. It is very important for mechanical. It is very important for piping. It is very important for electrical also. For all disciplines, even civil gets input from this. You have, let's say, a sump where you have acid-alkali lining, that volume of that sump that is required for the civil. That all is represented in this equipment list. Then instrumentation process data sheet. This is another very important document which is prepared by the process engineer. It's called IPDS. For all these items, the IPDS is produced. Then I'm just going to elaborate on the pressure control and instrumentation. Local gauges, pressure, temperature, flow level. What are the elements used? The remote gauges. What are the sensing elements used, as you can see. Control valves and types. This is also very important for process engineer. He has to choose the control valve type. As you can see, for throttling is different, and isolations are different types of valves used. Type of process control. So there are different types of process control. 5 types: feedback, feed forward, ratio control, split range, and cascade type. So feedback control. Now, as you can see, the feedback control, through the exchanger, the process stream has entered. At the outlet, you have the temperature sensor. So if the temperature sensor, suppose you are set at 80 degrees, if it becomes 82, feedback goes to the control valve steam valve is reduced and 82 becomes 80 again. This has a negative because there is some lag in the control. Okay, so this is where the feed forward system is better. Process engineer defines these systems. So in feed forward system, for example, in the exchanger, your steam is coming at 50 degrees, you are heating to 80 degrees. Let's say the inlet steam from 58 becomes 52. So this 52 then sends a signal to the steam, you reduce. So that means your outlet parameter 80 is maintained at 80 throughout. This is the advantage of a feed forward system. Your lag time is reduced. So your final process outlet temperature is more uniformly maintained in a feed forward control. But then you have to know the variability of the upstream temperature in order to finalize this. Cascade control. Here you see the fundamental control is the pressure of the fuel gas going into the fired heater. Okay. The slave loop is the pressure controller of the fuel gas. The temperature control is, the final is you are controlling the hot oil temperature, leaving the fired heater. That is the final control, desired control. So there the temperature transmitter is the master controller is sending a signal to the slave controller. If the temperature goes up of the hot oil, it will send a signal, reduce the pressure of fuel gas. So fuel gas cycle close. This is a cascade control. Split range control is also there. Let's say the reactor is there, you are controlling at 80 degrees centigrade. Now 80, it's an exothermic reaction, 80 becomes 82. What will happen is, the split range controller will send a signal, it will reduce the hot oil valve, it will reduce the hot water valve, it will open the cold valve. So this is a split range control to maintain 80 degree in the reactor. Ratio control. Now the ratio control in our last project, we had put up a hydrogen plant, a typical example I am giving. So the natural gas was the common fuel existing, which was going into the fired heater, and a hydrogen plant was put additionally to make it a green energy. So we were supplying 15% volumetric hydrogen into the natural gas line. So we had put a ratio control of the hydrogen line. Okay, so there was a control valve along with a flow transmitter on the control flow, which is hydrogen flow. Natural gas flow was being measured, which is uncontrolled flow. So suppose natural gas is 100 nm3, it will send a signal to the hydrogen FFIC that you throttle the valve to 15 volumetric %. So the control valve will throttle and you will get 15 nm3 going into the total flow. So this is the ratio control basically. So now process control of different rotating equipment. I am not going to go too deep into this. I am explaining this in quite detail in the later advanced course. Centrifugal pumps have different types of controls depending on requirement. Process engineers specify this. PD pumps are there. Reciprocating compressors are there. Centrifugal compressors are there. Different controls are there depending on process requirement. Rotary compressors are there. Different strategies are adopted for how the process controller wants the control. So it is very important. Please remember, process engineer decides this. Okay, he is central to deciding this. Now, typical distillation column controls, what are there? Feed flow control is there. Then you have the reflux inert gases outlet has a PC control at the top. Reflux drum bottom pump has a reflux flow control valve, which is cascaded to the column temperature, as you can see in the middle. Then the distillate top has a level control. These are typical distillation column controls. Steam at the reboiler at the bottom, steam is there in the flow control. The steam can also be cascaded to column temperature. Okay. Then at the bottom, you have a level control for the bottom product. So this is a typical feed process control. Again, a distillation column has more than 10, 12 types of controls. I'm going to elaborate this in the advanced course in detail. Safety studies, special process studies. So these are the safety studies. So process engineer on the left, you see, in the feed stage or detail engineering stage, all of these studies are done by the technical safety engineer. Process engineer, however, has to participate in all of these. Special process study on the right, you see flow assurance of a two-phase line coming, let's say, from far distance, crude line. Flow assurance is required, done in Olga, which is a very expensive software. Surge analysis is done. RAM study is done, where you need a continuity in the plant. RAM study is very important. The process engineer is responsible for studies on the right-hand side. Material of construction. Now, briefly, I'm going to cover here the different metallic materials available. Carbon steel, LTCS, low alloy steels, austenitic SS, which is 304, 316, duplex SS, which is used, let's say, in seawater service, super duplex is used, non-ferrous alloys are there. So again, metallurgical engineer will choose this. process engineer is also heavily involved in telling the metallurgical engineer what are the compositions of the streams, so that proper choice can be made. Non-metallic materials, as you can see, many types are there. So this item number 5 and 6, FEP and PFE are different grades of PTFE. PTFE is not moldable. FEP and PFA are moldable grades of PTFE. Then material construction for few common utilities I am giving here. Now here you see raw water is normally carbon steel. Potable water is GI, galvanized iron, which does not corrode. Okay. So, but only thing is potable water GI has a drawback because you cannot weld a GI. So you have to have union couplings in the middle. So at the bottom you see instrument air also is a GI. Okay. So there is a chance of leakage occurring in union couplings because it is a screwed fitting union coupling. So nowadays all major clients, they go with SS304 for the instrument piping also. Then the relative cost of the different grades you can see. Carbon steel, if you take one, just see at the bottom SS316 6.5 types of carbon steel. Okay, this gives you a relative idea. Pre-commissioning, commissioning. Now, pre-commissioning is a very important for the process engineer. He is central to this, and the process engineer who designs the plant, if he does the pre-commissioning, it is a cream of his job because he exactly understands what design he has done, and now he has to start the plant, run it. So, what mistakes he has done will also come to highlight to him. Now, for a small plant, pre-commissioning, commissioning can be done at one go. So, for a large, let's say the refinery plant where you have multiple units, you may be required to stagger it basically. So, there is an overlap occurring. So, at the top is a single plant where you can have it in distinct stages. Okay. At the bottom, there is an overlap for large plants. Like, for example, in my past, I had done a project where we had 3 plants, a polychloroprid rubber. So that was the final finished product. So you had chloroprene monomer, which was the first plant, continuous. Second was the polymerization plant, which was batch. Third was the finishing plant, which was continuous. And the utility is connected. So first you can commission the monomer plant. Meanwhile, the polymer plant can be doing pre-commissioning. Finishing plant can be under construction also. CMOP study has to still be done for this. So after monomer is commissioned, you can store it in the tank. By that time, you can start the commissioning of the polymer plant. So that's the staggering I'm talking about, basically. So these are the different activities in pre-commissioning, commissioning, preparation, planning. Second is mechanical completion. Third is pre-commissioning, operating. I have kept a special session for this in the advanced course. Here I'm not going to go into too many details in this. It's a field by itself, basically. Startup and initial operation, performance acceptance testing, post-commissioning. So here now, I sincerely hope my fellow engineers who have participated have benefited and have learned whatever I could elaborate on, and I hope it helps them in their career going forward. I would very much request them to increase your knowledge. It is very much required. In my day, knowledge came by the hard way, basically, and it took me many years to understand a lot of things which I am now elaborating to you. But you can do this at one go, and I'm sure it will benefit you a lot and save you a lot of time further going on also.